Night gathers in quiet layers, not merely the darkness of a sunless field, but the deeper hush that belongs to intergalactic space, a place where light must labor for billions of years to arrive. In that hush, a faint signal rises. It is not a shout, not even a full voice. It is the soft exhale of first starlight, slipping through primordial fog, a whisper that has crossed an ocean of expansion to meet a listening mirror. The instrument that receives it does not blink. It waits in a balanced cold far from Earth, its petals tuned to warmth that flickers just above absolute zero, its focus kept by actuators the size of seeds. The cosmos speaks in photons, and the message is old, older than any story written by human hands. The message says that there was a beginning, and that the beginning learned to shine. He sits in darkness, this patient hunter of early light, facing a sky that is no longer a dome, but a time machine. The airless gulf around him keeps silence so clean that a single thermal tremor would be as obvious as thunder. He looks not for familiar spirals, not for well-fed galaxies with arms like silver rivers, but for a subtler signature. He searches for the fine glow that lingers when hydrogen, once neutral and thick as fog in a harbor, begins to clear. That clearing is not a single event. It is a gradual lifting as the first generations of stars and nascent black holes pour ultraviolet light into the cosmic medium, heat it, ionize it, carve out transparent bubbles. He is tuned to the long wavelengths that climb out of that ancient struggle, stretched by expansion into red and infrared. The spectrum carries fingerprints that tell of chemistry just beginning to happen, of metals that did not exist until a star erupted and died. What does a whisper at first light sound like when translated into color and line, into graphs traced on screens in midnight control rooms? It sounds like a rising cliff at a particular wavelength, a feature astronomers call a break, where photons below a threshold disappear into the history of hydrogen. It sounds like a line etched thin as a reed, the trace of an element forging its first bonds inside a furnace lit by gravity. From such traces, the age of a galaxy can be estimated, its distance marked, its rate of star formation guessed by the brightness pouring from its young stars. The whisper speaks in numbers, in redshifts that climb into double digits, in luminosities that seem audacious for such a young universe. Yet the tone remains gentle, as if aware that comprehension arrives only when the mind slows down enough to match the pace of light. He gathers a field in a single gaze, the way a long exposure gathers city light into gold rivers. But here the rivers are time. Each fleck in the image is a memory pulled taut by the expansion of space. A few are foreground neighbors, most are pilgrims from a past so distant that the Milky Way had not yet found its shape. Some appear as smudges so faint that the difference between existence and illusion clings to a single photon captured at the end of a long chain of probabilities. Yet the instrument keeps faith with the improbable. It stacks the moments, collects the faint, and builds from almost nothing a portrait of the first morning. To ask what the telescope saw at the dawn of time is to ask how beginnings reveal themselves. Beginnings rarely arrive like trumpets. They arrive in hairline gradients, in the way darkness becomes grain, then glow. The early universe was dense and simple. Hydrogen and helium drifted in vast oceans, cooling, pooling, flirting with collapse. Quantum ripples seeded the map. Gravity thickened the seeds, and filaments of matter stretched like the skeleton of a future web. The first stars did not inherit metals from previous generations. They were pristine, massive, perhaps short-lived, their radiation severe, their deaths violent enough to forge the heavy elements that later worlds would need. The whisper that reaches the cold mirror carries the rumor of those lives. It brings news that the quiet was brief, that the universe found a way to ignite. In the quiet chamber where data becomes sight, a screen fills with galaxies that look like commas written by a patient hand. Some lie behind clusters whose gravitational fields curve space, turning the clusters into lenses that magnify the distant background. In those arcs, the whisper grows louder, not in volume but in clarity, as if the universe itself wanted these first structures to be seen. The telescope registers the shapes and colors, then passes the baton to instruments that split the light into threads, each thread a story of atoms and motion. The narrative of early time is not told in a single image. It is assembled from spectra, from calibrations, from the careful subtraction of noise. The process resembles listening for a heartbeat in a storm, then finding that the beat maps the life of a cosmos that is just learning to breathe. He faces a paradox of sight. To look far is to look young. The signal that arrives today left when space was small and the future unwritten. The phrase dawn of time appeals to poetry, yet the physics is specific. There was a radiant afterglow released when the universe cooled enough for neutral atoms to form, the background that fills the sky with microwave light. Later, long after that glow, came the first stars. Their light struggled through a fog of hydrogen until it carved clearings. The transition from fog to transparency is etched in the spectra as a cliff where photons vanish. The telescope is tuned to find those cliffs at wavelengths that depend on how far the light has been stretched by expansion. The more it is stretched, the earlier the origin. The earliest are the faintest, and the faintest are the most fragile against confusion. Yet in the patient coaddition of exposures, features emerge. The whisper sharpens. He hears consequence in that sharpening. If first light appears brighter than expected, if young galaxies are already rich in stars, then time must have been busy in ways models did not fully anticipate. If dust appears earlier than thought, then death and rebirth of massive stars must have been rapid. A whisper can carry urgency. It can say that the recipe for cosmic dawn includes ingredients that are familiar yet combined in surprising proportions. It can hint at black holes forming quickly, at seeds that either began heavy or fed so efficiently that mass bloomed like a storm-fed river. The instrument does not rush to judgment. It gathers longer, compares fields, cross-checks with other eyes on the sky. The whisper remains, but it gains texture, like a breeze turning into a pattern of ripples on a lake. He turns to the deep fields, those patient windows left open for days and weeks, and there the whisper becomes a chorus of tiny forms. Some are red, like banked coals. Others are almost colorless, their radiation stretched so severely that only the longest wavelengths survive. A few are lensed into arcs that encircle the mass in the foreground. The pattern is not random. It reveals a cosmos where structure grew along filaments, where the first cities of stars settled in the nodes of a cosmic web. It shows that gravity wastes no time, that even in youth the universe was already organizing itself into architecture. He does not treat the sight as spectacle alone. The beauty is obvious, yet he is trained to read beyond beauty. He asks what star formation rates could produce such brightness, what initial mass functions might favor massive stars, what feedback would heat or cool the gas, whether the faint glow at certain wavelengths could signal the presence of molecules formed in cooling clouds. He asks which lines in the spectra mark oxygen, carbon, or neon, and what those lines imply about early enrichment. He asks whether a compact source in the center could be a growing black hole, its light filtered through dust, its appetite altering the balance of its host. And still the tone remains gentle, the cadence close to a lullaby. The whisper of first light is not a challenge thrown down by the universe. It is an invitation. It invites a species that learned to grind mirrors and cradle them in space to step closer to its own beginnings. It invites patience. It invites imagination, anchored to evidence. It invites reverence for the way small signals survive vast journeys, how a photon birthed in a star that lived for just a few million years can travel for 13 billion and more, cross the drifts of dark matter, slide past clusters that bend its path, and finally settle into a detector that counts single quanta and tells a human mind that it has been found. What the telescope saw at the dawn of time is not a single object, not a single frame. It saw a threshold. It saw first morning as a living gradient, lit by stars that formed from the simplest gas, enriched by deaths that seeded future worlds, organized by gravity that sculpts without rest. It saw the universe remembering how to shine, and in that memory it offered a mirror to the species that asked the question. In the quiet far from Earth, the instrument keeps listening. The whisper continues, patient and old, as if first light never stopped speaking, only waited for an ear attentive enough to hear. A mirror is taught to bloom in cold space. It begins as ore lifted from ancient rock, refined into beryllium for lightness and stiffness, sculpted into 18 hexagons that hold their figure in deep chill. Each segment is polished until surface errors fall below a fraction of a wavelength, then dressed with a skin of gold to favor infrared light. Together they form a honeycomb that can fold like an insect's wings for the climb to orbit. The design is precise because the path is unforgiving. Every hinge must find its angle, every actuator must whisper its motion, and every surface must remember its intended curvature when the temperature falls from factory air to a darkness colder than winter's memory. A rocket waits on a tropical coast. The payload fairing closes, the clamps slide into their mechanical vows, and the countdown flows through checklists that took decades to write. At ignition, the vehicle sets a column of flame upon the Earth and reshapes gravity into ascent. A silver sea lies below, a violet sky ahead, and the guidance computer works through its equations as if reciting scripture. Separation comes as a clean gesture. The observatory drifts free of the upper stage, swings a small maneuver, and begins its own long journey. The destination is a gravitational balance point near the night side of Earth, a place called L2 that lies 1.5 million kilometers from home. There, the Sun, Earth, and Moon can be kept on one side of a heat shield, and the universe can be kept on the other. A membrane the size of a tennis court is asked to bloom. It is built from 5 sheets of kapton with aluminum and silicon coatings, each layer separated by small gaps so that heat can escape sideways and forward instead of leaking inward. The layers crinkle and restack during launch, restrained by hundreds of release devices. After days of quiet burns and small rotations, pins pop and covers pivot, tensioning cables draw tight, and the shimmering planes unfurl into their design. The first layer faces the sun and grows warm. The 5th layer faces the night and grows cold. Between them, a ladder of temperature drops is established, like descending terraces that carry heat away until the mirror floats near 40 kelvins. The process is measured by sensors that read in decimals, by engineers who follow the numbers with steady voices, and by a public that has learned to hold breath for unwinding miracles. The primary mirror opens in 2 wings. Each wing rotates outward, settles at its hinge stops, and locks. Now the honeycomb is complete. Under the gold skins, ice-cold beryllium holds its figure. On the back of each segment, small motors stand ready. They can tilt a facet by microns, push or pull its center by nanometers, and shape the collective into a single optical surface. This is the choreography called wavefront sensing and control. It begins with a star, a bright point chosen for its isolation. The blurred images of that one star appear 18 times on the first focused frames, each an imprint from a different segment. Algorithms match segment to sparkle, command a small nudge, then ask the system to look again. Over days, the 18 images migrate toward each other, then merge, then sharpen as curvature is tuned. A star becomes a needle point. The mirror becomes a single eye. Instruments wait in the shadow. A near-infrared camera lives behind the gold honeycomb. It is tuned to wavelengths where ancient galaxies speak most clearly, to colors stretched by cosmic expansion into red and beyond. A spectrograph nearby can slice that light into delicate combs of lines where chemistry and motion write their signatures. A fine guidance sensor keeps the observatory steady, correcting tiny jitters so that long exposures remain clean. A second spectrograph contributed by a partner agency watches in the same band, mapping thousands of spectra at once through microshutters smaller than grains of sand. Farther back, a mid-infrared eye rests behind a cryocooler that drives its detectors towards 7 kelvins. That deeper cold lets it hear the heat of dust and molecules, the glow of star-forming clouds, and the amber afterglow of planet-forming disks. Each instrument carries coronagraphs and filters, each carries wheels that spin with crisp clicks, and each carries memory enough to hold the sky until ground stations can listen. Calibration begins with the language of dark. Detectors are tested with no light, searched for bad pixels, and mapped for patterns of thermal emission. Lamps inside the instrument compartment simulate starlight, write standard lines across the sensors, and let software learn how to subtract the instrument's own fingerprint. Sky fields are chosen for the absence of bright stars, so that faint backgrounds can be measured with care. The point spread function is modeled across the field, a map of how a single point is spread by the optics into a small, predictable shape. This shape will be the yardstick for every faint detection, measuring sharpness, separation, and the hint of structure invisible to hurried eyes. The orbit around L2 is not a point, but a wide halo that lets the craft keep its antennae toward Earth without pointing itself toward the Sunday. Small thrusters trim momentum from reaction wheels and hold the path steady. Thermal sensors report a stable cold. Sun sensors confirm a constant angle to the light. The heat shield behaves exactly as predicted, casting a permanent night upon the mirror. The observatory is not stationary, yet it feels like a monastery of motion where all kinetics serve the silence needed for seeing. Teams that built the pieces become a single mind. A lab that grew the beryllium crystals remembers the cold ovens where the segments took their curves. A company that stitched the membrane remembers the day the clean room learned to hold its breath. A center that wrote the wavefront software remembers the dry run where simulated stars drifted into one. A European launch complex remembers the morning when a holiday became a window. A Canadian sensor remembers the first lock on a guide star. Many nations are braided into this machine. Many years are braided into the checklists that keep it calm when the sun sneezes or a micrometeoroid draws a white line through the quiet. Earth sends targets, and the observatory learns its dance. Slew, settle, guide, expose, dither, expose, calibrate, download. The rhythm becomes muscle memory for a machine. Dithering shifts the field by small steps to average out pixel quirks and to sharpen the final mosaic. Exposures stack like geological layers, each an era of photons collected in patient sums. Compressions save bandwidth without bruising the science. Downlinks drop torrents of data into dishes that drink starlight by proxy. Archive software catches the fall and arranges the streams into files that can be opened in 100 laboratories. No one person owns first light from a modern observatory. Time is allocated to programs that were proposed years before the launch, selected by committees that balanced ambition, feasibility, and the spread of discovery across many questions. Yet the first images that show the full power of the mirror are chosen not for exclusivity, but for demonstration. A cluster is imaged to let gravity turn the universe into a lens. A nursery is imaged to let dust glow like stained glass. A dying star's shells are imaged to show chemistry sculpted by wind. A planet outside the solar system is measured to show that a small dip in starlight can be turned into a spectrum, that molecules can be named in worlds never seen directly. These choices make a promise. If the machine can do this quickly, it can do much more slowly and deeply. Details that once sounded like hyperbole become routine. The mirror collects more light than any infrared observatory that came before it in space. The field of view is large enough to frame many galaxies at once. The sensitivity is such that a photon that left when the first structures were forming can end its journey as a single click in a detector cell. The angular resolution resolves star clusters in remote systems, separates knots in spiral arms, and traces arcs stretched by intervening mass. The mid-infrared eye sees the heat of dust and the blue ghosts of molecular lines. Together they cover a wavelength range that can read the full diary of early objects, from the ultraviolet light of hot stars shifted into red, to the thermal glow of dust trapped in newborn galaxies. The mirror has unfolded, yet the unfolding continues in another sense. Each observation teaches the team more about the instrument's behavior. Each calibration refines the flat fields that remove subtle declivities in sensitivity. Each thermal cycle reveals how the structure breathes when it slews from one attitude to another. A tiny micrometeoroid strike produces a measurable change in a segment's figure, and the actuators correct it. The mirror is alive in the way a musical instrument is alive, sensitive to touch, capable of being tuned after travel, dedicated to the accuracy that science requires. A question often asked before the launch becomes a statement afterward. The machine can hear the oldest light that galaxies can give, provided those galaxies were bright enough or magnified enough to survive their long journey through expansion. It can split that light into precise spectra and read redshifts well into an era when the universe was a fraction of its current age. It can detect the chemical fingerprints that mark the first rounds of enrichment. It can track the heat of dust that forms in the wake of violent lives. It can find the quiet glow that remains when a gas cloud begins to choose star from silence. A mirror unfolds in darkness and changes what is possible. It turns careful engineering into a new sense, one that hears warmth where eyes see black. It makes a home in the cold shadow of its own shield, then faces the sky with patient curiosity. The unfolding is not only a mechanical event, it is an opening in understanding, the end of rehearsal, the first true breath of a tool born to listen where the universe first tried to speak. A window opens onto a field that looks humble at first glance. A scatter of faint points trembles against velvet black, nothing like the bright anatomy of a familiar spiral. Yet the exposure is long, and the instrument is patient, and patience reveals history. The view compresses an epoch into a single mosaic. A cluster of galaxies in the foreground curves space enough to magnify the background, and the magnified background is a thicket of embryonic systems. Some appear as tiny rubies, others as barely resolved knots, some as arcs stretched into fine commas by gravity. The eye recognizes no constellations here. It reads something older. It reads time made visible. The camera works in colors too long for unaided sight. These are wavelengths warmed by distance, light once blue or ultraviolet from young stars now shifted into red. Detectors cooled to near-perfect stillness trap those photons with exquisite efficiency. The sky is dithered in small steps, exposures stack in deep layers, and the noise declines like surf at slack tide. With enough accumulation, the improbable becomes evident. Objects that once hid below the threshold of detection lift above it with a small but measurable certainty. In each faint glow is a record of stars that burned when the universe had scarcely discovered structure. The immediate question is distance. In cosmology, distance is told by stretch. The spectrum of a source is laid out, and familiar features slide toward the red in proportion to the expansion of space. For very dim sources, a full spectrum is not always possible. The image itself, taken through multiple filters, becomes a surrogate measure. At a particular rest wavelength, neutral hydrogen in the intergalactic medium absorbs hard, carving a boundary in the spectral energy distribution. That boundary, if moved to longer wavelengths by expansion, causes a vanishing of flux in the bluer filters and a survival in the redder ones. Astronomers call the method a dropout selection. It is elegant because it translates an absence into a signpost. A small galaxy that disappears in one channel and appears in the next tells a story of how far its light has traveled. When a spectrum can be drawn, the tail deepens. A narrow spike may pierce the red side, a line born in the hearts of star, forming regions where ionized hydrogen recombines and radiates. The intergalactic fog can mute that line or scatter it, but when it survives, it gives a precise measure of distance and a hint of the surrounding medium. Other lines carve their own signatures. The presence of oxygen or carbon tells that massive stars have already lived and died, releasing their products to season the gas. The width of a line suggests motion within the galaxy, whether tranquil or turbulent, whether rotating or stirred by feedback. The first canvases of this era astonish with richness. A single deep field frames thousands of galaxies at once. Many are mature in the middle distances, filled with dust lanes and spiral grace. Others are smaller and clumpier, evidence of building rather than finished form. The very faintest flicker at the edge of detection is often the most compelling. If that whisper is real, it corresponds to a population present when the universe measured a small fraction of its current age. Confirmation requires care. Photometry from independent reductions must agree within uncertainties. Spectroscopic follow-up must survive the thin harvest of photons. Tiny systematic errors in calibration must be chased down and corrected so that a dim point cannot pretend to be ancient simply because a flat field was imperfect. Gravitational lensing becomes an ally. A massive galaxy cluster bends space like glass with a curved surface, distorting and brightening whatever lies behind. The geometry produces multiple images of the same distant source, each image arriving along a different path. The paths differ in length and in the potential they traverse, so time itself is slightly offset between them. Identifying these repeats offers a powerful cross-check. If two smudges share the same microscopic structure and color, then they are likely one object seen twice. Modeling the mass distribution of the lens then yields a magnification, without which intrinsic luminosity cannot be deduced. Such modeling demands precise positions for many lensed features, and the sharpness of the image makes those positions available. The star-forming vigor, implied by some of the bright red smudges, invites immediate calculation. Given the measured flux at specific wavelengths, given the assumed initial distribution of stellar masses, one can estimate how many suns per year are igniting in a system a fraction the size of a modern spiral. The numbers can be surprisingly high. Massive stars live briefly and pour ultraviolet light into their neighborhoods. That light escapes or is trapped depending on the geometry and dust content of the surrounding gas. If trapped, it warms grains that in turn glow in mid-infrared bands. If escaping, it helps carve ionized bubbles in the intergalactic medium. The ratio of these outcomes shapes the appearance of each object across filters, and a consistent model must fit them all. The vision of a stellar nursery in a nearby region adds a different layer of context. Jets spear from infant stars. Cavities carved by outflows and radiation open like stained glass windows cut in dust. Shock waves ring the voids, thin and bright. These scenes demonstrate how light and wind sculpt matter. The same physics scaled up with lowered metallicity would have operated in the youth of the cosmos. The images of nearby nurseries therefore serve as teaching diagrams for the more distant and unresolved sources. They are not analogies alone. They are laboratories that tune expectations, anchor models, and supply intuition when interpretation of faint ancient signals walks along a blade of uncertainty. A dying star's shroud in a local system brightens the mid-infrared camera with concentric shells. Chemistry rides on those shells. Silicates and carbon compounds trace the pathways by which elements born in cores and supernovae condense into dust. The presence of dust in very early galaxies implies that massive stars lived and ended swiftly. The glow of dust therefore becomes an independent clock. If dust is abundant when the universe is young, enrichment must be rapid, and star formation must have been vigorous enough to feed that enrichment. The distant fields and the local laboratories together turn images into a chronology of the first cycles of creation and dispersal. A compact knot that coincides with a rise in certain spectral features may hint at a growing black hole. Accretion of gas onto a massive central object produces hard radiation and can drive winds that heat and evacuate surrounding material. Patterns in the mid-infrared, combined with high ionization lines in the near-infrared, build a case for such activity. If confirmation follows, the implication is profound. It suggests that black hole seeds either formed with substantial mass or found a way to feed at rates that challenge conservative assumptions. The visual evidence is only a beginning. Temporal analysis looks for flicker. Comparisons across wavelengths chase the distinct signatures of star formation and accretion. Step by step, the portrait becomes clearer. The sharpness of the images reveals structure within small galaxies that once appeared as single blobs. Clumps separate from clumps. Tidal features hint at mergers. Chains of knots align along what might be a filament of infall. Sizes measured in kiloparsecs shrink toward values expected for systems assembling in a denser universe. Surface brightness dims with redshift in a severe geometric manner, but the sensitivity here is enough to bite into that dimming and still retrieve form. Such morphological insights feed back into theories of how gas cools, fragments, and turns into stars under different pressures and metallicities. A quiet but critical effort accompanies the dramatic scenes. Backgrounds must be understood precisely. Zodiacal light, stray thermal emission, faint scattered starlight, detector persistence, and cosmic ray hits all conspire to paint unwanted textures on a frame. Sophisticated pipelines model each component, subtract what is understood, and flag what is not. Artificial sources are injected into raw frames at known positions and brightness, then recovered by the same algorithms used for science, in order to calibrate completeness and bias. The final catalogues of positions, fluxes, shapes, and photometric redshifts are accompanied by careful uncertainties. Beauty attracts attention, but rigor wins knowledge. Selections from multiple deep programs begin to sketch a census. Blind surveys map small regions to extraordinary depth. Lens-assisted campaigns trade area for magnification and harvest sources that would otherwise be invisible. Parallel fields, taken while primary targets occupy one instrument, extend the sampling without cost in time. The result is a matrix of look-back, sensitivity, and environment. Within that matrix are the earliest candidates that merit confirmation. Every such candidate triggers a chain of follow-up with slit and prism modes, with low and medium spectral resolution, with careful planning to avoid contamination from neighboring objects. The reward is a single, unambiguous feature, pinned to a redshift that places the galaxy within the first few 100 million years of cosmic time. The first glimpses across 13 billion years are quiet, yet transformative. They do not overturn physics. They refine it by specifying how quickly the first structures gathered, how fiercely they formed stars, how fast dust and metals appeared, and where gravity's lens reveals sources too faint to be otherwise seen. The view proves that a single frame can hold a gallery of epochs. It shows that a mirror held in deep cold can turn absence into measurement and faintness into narrative. It teaches that the sky is not a backdrop but an archive. Each pixel is a paragraph, each arc a footnote in curved geometry, each dropout a signature of distance, each spectrum a stitched memory of atoms speaking across expansion. In the control centers and data labs, the response to these images is twofold. Awe is allowed to breathe for a moment while the mind adapts to the depth of what is shown. Then the benchmarks are set. Sensitivities are logged, limiting magnitudes verified, color selections validated, completeness assessed, recovery fractions plotted, and data products released to a community ready to turn pictures into history. A small patch of sky teaches how the first morning grew busy. It tells of building, brightening, and being seen. The first glimpses are not the end of inquiry. They are the map that makes inquiry possible. Numbers arrive that do not sit quietly. They arrive as photometry converted into mass, as sizes measured in kiloparsecs, as star formation rates that read like wild weather. The portraits of small red smudges are translated into physical quantities, and some of those quantities appear to outrun the calendar. A handful of galaxies look heavy for their youth. Their light implies stocks of stars already built when time was still learning its clockwork. The phrase, "too big, too soon," rises not as a slogan but as a question. How can a universe that begins in smooth simplicity arrange so much mass into such tight rooms so quickly? The instruments are not surprised by brightness. They are surprised by how brightness converts to mass and by how little room exists on the early timeline to grow it. The method is disciplined. A shape in the image is measured across filters that sample several points along its spectral energy distribution. The colors, along with a redshift from lines or break positions, feed population synthesis models that compare observed fluxes to libraries of theoretical stellar mixes. Outcome estimates of stellar mass, ages, and recent rates of star formation. The uncertainties are real, yet even with those bands of doubt, some sources land in a region that strains expectations. A compact system of a few hundred parsecs may appear to hold 1 billion suns in stars. Another, only slightly larger, may push higher. Multiply by several such objects in a small survey, and the ratios begin to talk. They tell of halos that must have gathered gas with a rare efficiency, of clouds that must have shed angular momentum with ruthless speed, of cooling that must have been faster than temperate models predict. The tension is not with gravity itself. Gravity is patient and implacable. The tension is with the supply of time and with the rules that translate dark structure into luminous structure. The standard framework expects the number of heavy halos to fall steeply toward early times. Inside those halos, gas should cool and collapse, but not with perfect economy. Supernovae should stir and heat the medium. Radiation should push back on infalling gas. Turbulence should disrupt the most efficient collapse, and the first metals should alter the cooling channels. These feedbacks keep star formation from devouring the reservoir too fast. The early census seems to include examples where restraint did not win. Immediate counter-arguments are healthy. Perhaps the mass-to-light ratios are overestimated because the stellar populations contain more young hot stars than the models assume. Perhaps nebula emission contributes more to certain filters, causing inferred continua to swell. Perhaps dust reddening has been mischaracterized, masking youth as maturity. In some cases, active nuclei might add featureless radiation that masquerades as stellar light. Gravitational lensing may have magnified some sources more than preliminary models suggest, inflating luminosity and therefore mass. Photometric redshifts can be fooled by unusual spectra, placing a closer object at an apparent greater distance. Teams revisit each possibility with care, adjusting models, adding priors, remeasuring fluxes, and pursuing spectra with better signal-to-noise. Even with caution, a subset of candidates remains stubborn. Where lines pin the redshift firmly, where lensing is negligible, and where corrections for emission and dust have been applied, the masses still hover high. The sizes are small, implying high surface densities of stars and gas. Star formation rates, inferred from ultraviolet luminosity, or nebula lines, can reach tens or hundreds of solar masses per year in objects barely larger than globular clusters. Such rates, if sustained, build up the claimed masses on cosmic timescales that fit, but they require near-continuous fueling and a platform that resists disruption. The visual morphologies sometimes show clumps that could be merging subunits, a plausible route to rapid growth in crowded filaments. The ultraviolet luminosity function, which counts galaxies by brightness at these early times, looks steep at the faint end and surprisingly populated at the bright end. The bright tail is where too big, too soon draws attention. Each luminous point is rare, but over the surveyed volumes the statistics are still meaningful. If the bright end is amplified by a bias in selection or by scatter that promotes a few objects above the detection threshold, that must be measured. Eddington bias is the technical name for such promotion. Correcting it requires knowledge of the scatter itself, which early data cannot define perfectly. As deeper exposures accumulate and independent surveys cross-check, the shape of the function will settle. The preliminary suggestion remains that luminous systems were not as scarce as conservative models assumed. A related puzzle hangs on the early appearance of quiescent candidates. A quiescent galaxy is one whose star formation has tapered to a trickle, whose light is dominated by older stars with red colors not caused by dust. Finding even a small number of such systems when the universe was young places constraints on how briefly the starburst phase lasted and how quickly feedback or environmental effects could shut it down. If such halting required an active nucleus to heat or blow out gas, then black holes must have grown on matching schedules. If it required the exhaustion of fuel through extraordinary star formation efficiency, that efficiency must be explained with microphysics in dense, low metallicity gas. Theoretical responses pivot between conservative revision and bold speculation. One line explores the initial mass function of stars. If the earliest stellar populations were biased toward massive stars, then light per unit mass would be higher and inferred masses would come down. This idea fits the colder chemistry of metal-poor gas, where fragmentation may prefer larger clumps. Yet a top-heavy distribution reignites the problem of rapid enrichment and dust production, which, if observed, supports the same argument rather than erases it. Another line tests the duty cycle of starbursts. If observations catch systems in their most luminous moments more often than expected, then temporary bright phases could bias the sample. That explanation needs a mechanism to synchronize many bursts across different environments, which is a high bar. Accretion physics offers a path through the thicket. Cold streams of gas funneled along filaments can flow directly into halos, feeding galaxies at rates that overcome internal feedback. If streams are narrow and dense, they can slip past shocks and deposits of heated gas. Simulations that resolve such flows in a young universe predict compact, gas-rich disks that build stars in rings or clumps. The observed sizes and clumpiness fit such a picture. To reach the largest masses quickly, these inflows might need to be nearly continuous, or several galaxies along the same filament might merge in short order, stacking their reservoirs together. There is also the character of dark matter to consider. The standard cold and collisionless picture builds small structure first and grows larger halos through mergers. If dark matter had even a hint of warm character, the smallest halos would be suppressed, shifting early growth toward bigger seeds. That shift could make massive early galaxies more natural, but it would also alter structure on many other scales that are tested by other observations. Any change here must walk through a maze of constraints. The appeal of simplicity keeps the community near the standard map unless compulsion becomes strong. The conversation remains quantitative. Stellar surface density profiles are fitted to measure how compact the light is. Velocity dispersions, when obtainable from broadened spectral lines, check whether such compactness is matched by the expected gravitational potential. Star formation rate density across the universe is updated with each survey, tracing a curve that rises from the origin, peaks, and declines. Early points on that curve climb higher with the new detections. If they stay high, the integrated number of photons available to reionize the intergalactic medium increases, and the timeline of that transition tightens or shifts. Cross-checks with background radiation measurements sharpen the preferred histories. At human scale, the idea of too big, too soon invites metaphor. At cosmic scale, it invites a schedule. The schedule is written in simple ratios. A galaxy of 1 billion solar masses, at a redshift that places it a few 100 million years from the origin, must have averaged thousands of solar masses per year in inflow and formation over its assembly epoch, unless its growth was strongly punctuated. Momentum transport within the disk must have been efficient. Feedback must have carved rather than crushed, channeling gas into new stars rather than ejecting it entirely. Turbulence must have been sustained but not prohibitive. These statements are not romance. They are constraints that any successful theory must satisfy. The discipline of skepticism remains central. Each high-mass claim motivates fresh spectra, deeper imaging, and independent reductions. The stack of cases that survive those tests will define how much revision the models require. It is still possible that improved measurements will ease the tension, that systematic uncertainties are larger than first estimated, and that the survey volumes were lucky in their sampling of rare peaks. It is also possible that the early universe possessed a brief window of conditions that favored extraordinary efficiency, a window now being resolved with clarity. The count of massive early galaxies may not be an error. It may be an announcement. Too big, too soon becomes a lesson in how quickly structure can find itself in an expanding space. It points to the economy of gravity when supplied with cold gas and freefall. It binds theory to measurement with numbers that do not blush. It reminds that models are scaffolds rather than palaces. When data ask for more beams, more braces, and a wider span, the scaffold grows. The sky does not give contradictions, it gives invitations. Here the invitation is to revisit growth in a young and metal-poor environment, to test the efficiency of cooling and transport under conditions that have no nearby analogue, and to let the first cities of stars instruct the blueprint rather than obey it. Hydrogen keeps a quiet calendar. It marks time not with clocks but with its readiness to let light pass. When atoms are neutral, they behave like fog. Photons with energies above a threshold are bitten away, leaving a cliff in any spectrum that tries to cross. When atoms are ionized, they become transparent, and starlight travels with fewer interruptions. The infant universe shifted between these states, and that shift left signatures precise enough to be read from far after the fact. A telescope tuned to the right wavelengths finds those signatures as boundaries, hollows, and thin lines that carry the taste of early chemistry. The physics begins with a simple resonance. An electron bound to a proton can climb between levels, and the jump from the first excited state to the ground state emits or absorbs light at a specific ultraviolet wavelength. In a young cosmos filled with neutral atoms, that resonance turns the intergalactic medium into an absorber. Photons bluer than that line are scattered out of sight. As time passes and stars and newborn black holes pour ultraviolet radiation outward, surrounding hydrogen loses its electrons and becomes transparent. The transition is not abrupt everywhere. It happens in pockets that grow and merge, like dew evaporating from a field as the sun climbs. Spectra carry the news with delicate clarity. Light from a distant galaxy arrives stretched by expansion, so the ultraviolet signature slides into the infrared. A prism inside a spectrograph spreads that light into a smooth curve with features. On the blue side of the resonance, flux drops sharply. On the red side, it returns. The position of the drop fixes distance. The depth and slope whisper about the state of the medium between stars. If enough gas remains neutral along the path, the red side shows a broad wing where the resonance still reaches outward and steals photons. That shallow wing is a sensitive indicator of how much fog is left. It is written by physics that is indifferent to human hope, and so it is trusted. The geometry of ionized bubbles can be inferred from that trust. A galaxy that shines inside a bubble sends its spectral line through a clearer tunnel. The line survives more easily, grows higher above the continuum, and stands like a flag. A galaxy embedded in a region still rich in neutral atoms sends a line that is gnawed at the edges or erased entirely. By sampling many such sources at different distances, a map of ionized fraction versus time is built. It is a census of clearing days across the first morning, a diary of how hard young stars and mini-quasar engines worked to carve sightlines through the fog. Color alone can make a first cut when spectra are scarce. Photometry through several filters acts as a coarse spectrograph. The blue channel goes faint, the red channel remains, and the jump between them marks a candidate whose light moved across the resonance. The technique that treats absence as evidence fills catalogues with targets for deeper inspection. Once a slit or microshutter isolates the source, the full curve can be recorded. Even a weak detection of a line placed where the dropout predicted can tip the balance from candidate to confirmation. A single measured position, when multiplied across a field, becomes a timeline. Hydrogen also tells on motion. The spectral line broadens when gas swirls, rotates, or disperses under intense radiation. The shape of the profile, the symmetry, or skewness, carries information about outflows driven by star formation, about inflows along filaments, and about the damping imposed by the intergalactic medium. In compact high redshift systems, the line often skews to the red because photons trying to step to the blue are eaten by residual neutrality. A red tail therefore implies both local kinematics and the thickness of the path beyond the galaxy. Untangling the two requires models that treat radiative transfer through clumpy gas, but the reward is a physical story rather than a catalogue entry. Dust participates as a quiet partner. Grains absorb and re-emit, reshaping the spectral slope across the infrared. When the slope is steeply rising, the starlight is relatively unobscured and young. When it flattens or turns down, dust has taken its toll, or the stellar population has aged. In the context of reionization, dust sets how much ultraviolet light can escape a galaxy to do the work of clearing. The escape fraction becomes a critical parameter. High escape fraction implies that even modest star formation can ionize large surroundings. Low escape fraction shifts the burden to rarer star factories or to black hole accretion. Observations of far infrared lines from ionized carbon and of mid-infrared features from warm dust help constrain these balances. The color of hydrogen's world is therefore painted not only by atoms but by grains born in the deaths of massive stars. Gravity helps in a less obvious way. When a background galaxy is stretched by a foreground cluster, its flux increases and fine structure becomes accessible. Spectral lines that would be invisible without magnification climb above the noise. The environment of the lensed source can then be probed with unusual detail. Regions where star formation is concentrated may show stronger emission. Regions shadowed by dust pillar structures may show weaker line flux or altered profiles. By comparing multiple images of the same galaxy created by the lens, the consistency of features is tested across different paths through the intergalactic medium. Any discrepancy hints at small-scale variations in opacity along the separate routes, a subtle method of sampling the fog. Hydrogen signatures also relate to temperature. After ionization, free electrons and protons recapture each other in cooling pockets, emitting characteristic lines. The balance between collisional and radiative processes shifts with density and temperature, and that balance sets line ratios that can be measured. Ratios, in turn, reveal how hard the radiation illuminating a region must be. Soft fields produced by stars, and harder fields produced by accretion engines leave different footprints. When those footprints are tallied across early volumes, the contributors to reionization can be weighted. The Book of Hydrogen has chapters written by hot stars and by growing black holes, and their scripts can be distinguished. Beyond the spectral line itself, continua hold quiet information. The ultraviolet slope of a galaxy's light, when corrected for dust, translates into an age distribution of its stellar population. Very blue slopes suggest freshly minted stars and high production of photons capable of ionizing hydrogen. Redder slopes suggest maturity or dust. The faintest systems at high redshift often show strikingly blue slopes, bolstering the idea that swarms of small galaxies supplied a large fraction of ionizing photons. The bright end of the population, though rarer, may be less efficient per unit mass if dust blankets their cores. This division of labor between numerous small contributors and rare luminous beacons shapes the narrative of how the fog lifted. Foreground gas sometimes leaves its own marks. Absorption by intervening clouds imprints small notches at redder wavelengths than the resonance. These systems act like signposts along the line of sight. Counting them and measuring their strengths informs models of how quickly the intergalactic medium's islands of neutrality shrank. When such absorbers sit near the target galaxy, their influence becomes both local and instructive. They can signal satellite structures, outflow shells, or streams of inflowing material that carry cool gas into the halo. The interplay between a galaxy and its immediate circumgalactic medium emerges as crucial. It is the last barrier that escaping photons must cross before they join the wider clearing. All of these threads are measured, while geometry dims everything cruelly. Surface brightness falls with distance more rapidly than naive intuition expects. The instrument's cold detectors answer that cruelty with sensitivity and stability. Long integrations lower noise until a single, narrow feature can be trusted. Careful dithering fixes pixel quirks. Background subtraction untangles faint targets from faintly glowing skies. The craft of measurement is what grants the physics a clean page on which to write. Hydrogen's color, then, is not simply a hue. It is a code for state, for temperature, for ionization, for the presence of heavy elements that alter cooling pathways, for the vigor of star formation, for the possible touch of a black hole's hard light. Each distant spectrum adds a bead to a necklace that spans from opaque beginnings to a transparent day. When many beads are threaded and their spacings measured, a timeline appears that says when the average atom in the intergalactic sea chose to let light pass. That choice is the dawn. It is the first environmental transformation undertaken by stars and the engines at their centers. It sets the stage for all subsequent structure to be seen rather than hidden. The questions that remain are scaled to the sensitivity now available. How patchy was the fog at each moment? How much of the work was done by galaxies smaller than current surveys can resolve? How frequently did nascent black holes flash in brief, hard episodes that left disproportionate impact? How did metallicity alter the spectrum of early stars and the hardness of their output? Answers live in the details of line profiles, in the statistics of detection versus non-detection across matched samples, and in the union of infrared measurements with radio maps of the background from neutral hydrogen that still carries echoes at long wavelengths. The canvas is wide, but the brush is exquisitely fine. When hydrogen's calendar is read with care, time itself feels less like an abstraction and more like a change of state. The universe is not only expanding, it is learning to transmit. The shift from fog to window is recorded in spectra as surely as tree rings record winters. To listen is to watch darkness dilute and to measure the rate at which clarity spread. That rate tells how urgently the first furnaces burned, how cleanly their light escaped, and how soon space became a place where vision could reach across it without being swallowed whole. Faintness can feel like a rumor. It lives in the margin where a single photon changes the verdict from nothing to something. A camera chilled until its own warmth sleeps is asked to listen at that edge. Patterns are coaxed from noise by rituals of dithering and stacking. A field that looked empty grows freckles of possibility. The most intriguing are so dim that the mind hesitates to grant them reality. They are called ultra-faint for a reason. Their light has been stretched thin by expansion, diluted by geometry that darkens distant surfaces by a power of 4 in redshift, and softened by time itself. Yet there they sit, ghosts in the infrared, offering the first census of sources too modest to rule the scene but too numerous to be dismissed. Detection begins in the discipline of background. The sky is not truly black, even from a cold vantage far from Earth. Thermal whispers, zodiacal glow, scattered sunlight along the shield, detector drifts, and tiny scars left by cosmic rays all scribble on the frame. Pipelines trained to recognize these hands subtract and smooth without erasing what is fragile. Artificial galaxies with known shapes and brightness are planted into the raw data and then recovered by the same algorithms that will search for reality. Recovery fractions anchor the claims. Confusion is mapped and minimized. The remaining canvas is ready for hunting. At this threshold, shape is a luxury. Many candidates are mere knots, only a handful of pixels across. Their existence is asserted through consistent presence across filters where they should appear, and absence where neutral hydrogen should erase them. Photometric redshifts are assembled from a small set of colors, each with a large uncertainty. The probability that a given smudge is ancient rather than a nearby imposter is coded as a curve rather than a single number. Human habits favor a crisp distance, yet honesty keeps the curves. A population emerges not as a list of certainties, but as a distribution whose collective weight carries meaning. Imposters are persistent companions. Cool dwarf stars in the outskirts of the Milky Way can mimic the hues of redshifted galaxies. Their spectra are riddled with molecular bands that carve the same filters where the early universe dims. Tools that compare point-like shapes to broader profiles separate many of these stars from genuine distant fuzz. A few survive the cut and knead spectra to end the argument. Another class of imposters lives at modest distance, yet glows in extreme emission lines that fall in just the right filters to impersonate an ancient continuum. Medium-resolution spectra are the referee here. A true ghost of the early cosmos shows a deep break and sparse features. A masquerader shines with narrow lines that betray a far closer home. False positives arise from the instrument as well. Persistence from a bright source can leave a fading echo that looks like a faint galaxy, if not recognized. Fleeting artifacts with names that suggest their shapes, snowballs or wisps, can mimic structure. Calibrations tag their signatures and remove them, but vigilance stays high. Cross-checks between independent reductions become habits rather than favors. A candidate that survives competing pipelines grows more believable with each pass. Gravitational lensing steps in with its quiet gift. A massive cluster makes a curved glass of space. Behind that glass, tiny galaxies are stretched and amplified. The boost in brightness makes the otherwise unreachable visible. The price is distortion and the need for careful modeling. Maps of the lens are built from the positions of many arcs and from assumptions about how mass follows light or hides in dark halos. With a map, the image plane becomes a source plane. A knot near a caustic can leap in brightness by an order of magnitude. The same knot may appear twice or thrice. Agreement in color and microstructure marks twins. Time delays between images are small at these distances, yet the redundancy aids confidence and allows a reconstruction of intrinsic size that would otherwise be hopeless. Completeness is the constant worry. Ultra-faint means many are still missed. The detection threshold is not a wall but a slope. Variations in noise across the field, the chance overlap with a foreground speck, and the vagaries of the dither pattern all change the odds that a given ghost is recorded. Teams estimate the invisible population by counting the visible and scaling with the measured completeness. This is where simulated insertions earn their keep. Thousands of fake galaxies with plausible sizes and profiles are injected at random, then harvested by the same search routines. The ratio of planted to found writes the correction. The corrected counts become the faint end of the luminosity function, the part that dominates the raw number of sources, and often the production of ionizing photons. Stacking adds a new sense. Individually, many ghosts are below the level where meaningful colors can be measured. Together, aligned and averaged, their combined light speaks. The average ultraviolet slope of a stacked set suggests how young the stars are and how little dust intervenes. The presence or absence of a feeble line becomes detectable when summed over hundreds of similar objects. This ensemble approach sacrifices individuality for clarity. In the arithmetic of large numbers, attributes that define the population rise above noise, even when no single member can tell its own story in full. Fluctuation analysis reaches deeper still. Instead of looking for discrete objects, the image is treated as a field of tiny intensity variations. The power spectrum of those variations carries the imprint of countless sources too faint to pick out. If these sources cluster, as galaxies do along a cosmic web, their pattern adds power at scales that reflect that clustering. By modeling and subtracting all known contributors, the residue becomes a measurement of light from structures below the detection floor. Such studies can test whether a hidden army of tiny galaxies exists and whether it is bright enough to have mattered in reionization. It is a way of hearing a crowd behind a wall without opening the door. Surface brightness is the other unforgiving judge. Even if total luminosity is modestly high, if it is spread over a large area, the result can slide below detection. Early sources are often compact, which helps, but any extended halo of diffuse light is difficult to retrieve. Techniques that model and subtract the smooth glow of foreground galaxies, that correct for the wings of the point spread function, and that fit profiles to faint outskirts are required to see what lies beyond bright cores. In a few cases, diffuse intra-halo light appears like the first breath of structure around an infant system, perhaps the signature of tidal stirring or the early capture of companions. These ghosts are not only galaxies. Some may be star clusters on galactic scales, clumps that will later settle into larger hosts. Others could be transiently bright complexes, lit by short-lived massive stars. A minority may hide small, accreting black holes whose contribution to the light is subtle, detectable only through line ratios or faint mid-infrared excess. Distinguishing these subtypes is difficult when photons are scarce. It becomes a game of priors and probabilities, always checked against what spectra and lensing can reveal. Cosmic variance plays its familiar tune. A narrow, deep field can be unrepresentative if it happens to land on a region of space that is richer or poorer than average. Lensed fields sample very small source plane areas, prone to the moods of a single filament. Large programs respond by tiling many fields, by balancing blank regions with lenses, and by pooling results. The aim is a census that smooths the whims of structure and approaches the true mean universe. When the faintest census is charted, a pattern returns again and again. The number of tiny systems rises steeply toward lower luminosity. The slope is steep enough that the swarm of minuscule contributors may dominate the total ionizing budget, even though each member is humble. If these systems allow a generous fraction of hard photons to escape, then they become the backbone of the transition from fog to window. If their escape fraction is modest, the burden shifts back to rarer bright galaxies and accreting engines. Measurements of blue ultraviolet slopes at the faint end favor the efficient scenario, yet direct escapes are hard to prove. The debate stays alive in the data. Every claim of a record-breaking redshift draws special scrutiny. Photometric solutions at extreme distance can be confused by dusty mid-redshift imposters whose spectral breaks mimic the ancient edge. A line detection with secure placement ends the argument. New configurations of slitless and slit spectroscopy try to trap these lines without sacrificing precious time. When the line remains elusive, the weight of evidence is built from colors, morphology, and lensing geometry. The community learns to grant belief in graded ways. Robust candidate, strong candidate, plausible, interesting. The adjectives restrain certainty until a feature is pinned. In the quiet of long integrations, the ghosts continue to gather. They are not decoration, they are the scaffolding of the dawn. They reveal the scale on which gravity first braided gas into steady star birth. They show how much light was produced where no spectacle announces it. They test the edge of what an instrument can promise and what patience can deliver. In accepting their faintness as a condition rather than a flaw, the story of the earliest morning becomes a study in humility. The universe did not begin with monuments alone. It began with whispers that multiplied until they became a day. A dark heart can shine brighter than a galaxy. In the first few 100 million years, compact engines ignite at the centers of small systems, pouring hard radiation into environments still learning to cool. The engine is gravity-made incandescent. Gas falls toward a massive object, spirals inward through a disk, heats by friction, and radiates across the spectrum. The object can be a black hole with a mass that defies the youth around it. When such an engine feeds well, the continuum swells and high-energy photons escape, carving ionized cones through the surrounding medium. Starlight is no longer the only architect. Accretion adds a new hand to the blueprint. Clues to these engines appear first as lines that are too hard and too strong for stars alone. A near-infrared spectrum shows narrow spikes from ions that require energetic photons to exist. Triply ionized carbon draws a sharp mark. Helium that has lost one electron sings at a wavelength that demands a blistering field. Nitrogen in high charge states answers with its own sign. The ratios between these lines form a grammar. If the ratios tilt toward hardness, an accreting black hole is likely at work. Sometimes the spectrum broadens around hydrogen or magnesium features. The broadening speaks of gas racing close to an event horizon, velocities of thousands of kilometers per second, spreading the line into a wing. That wing is a signature difficult to counterfeit. Imaging adds context that a spectrum cannot show. The central knot can be more concentrated than the surrounding stellar body. Color maps betray a warm core with gradients that fade into cooler outskirts. Mid-infrared filters pick up the glow of dust heated by the engine and re-emitting at longer wavelengths. When that glow rises above what young stars would produce, a hidden nucleus is implicated. Polar structures in ionized gas hint at biconical outflows, the funnels through which radiation and wind escape. In fortunate cases, a field reveals extended emission aligned with such a cone, a faint brushstroke showing that the engine has begun to sculpt its neighborhood. Mass estimates follow cautiously. If a broad line is present, the width and the luminosity near the line feed empirical relations that return a black hole mass. The methods were trained in a later universe where reverberation mapping tracked time delays between changes in the continuum and in the lines. Those calibrations are carried back to youth with care. The results sometimes land in the millions to hundreds of millions of solar masses at redshifts that compress the available growth time. Such masses invite a story about the seed. A stellar remnant of a few dozen to a few hundred solar masses cannot easily reach those weights by steady feeding alone. Either the accretion rate exceeded the standard limit for long periods, or the seed began heavy, or mergers stacked mass quickly. Super Eddington accretion is one path through the dilemma. The Eddington limit balances radiation pressure against gravity for spherical symmetry and thin disks. In dense, optically thick flows, energy can be trapped and advected inward rather than radiated away promptly. The result is a slim disk whose luminosity grows more slowly than the accretion rate. Mass piles in faster than a naive calculation would permit. Simulations of such flows show collimated funnels that vent radiation, while allowing the bulk of the material to continue inward. If young galaxies fed their nuclei in such states repeatedly, the time budget relaxes. Direct collapse presents a different origin story. In certain halos bathed in intense external radiation, molecular hydrogen can be suppressed, preventing efficient cooling and fragmentation. Gas then collapses nearly isothermally until a supermassive star or quasi-star forms, unstable against collapse, into a black hole seed of 10,000 to a million solar masses. Such a seed, placed into a gas-rich environment, can approach the observed early masses with only moderate feeding. Traces of this pathway might include galaxies with extremely low metallicity around their centers, narrow ranges of stellar ages, and perhaps distinctive line ratios from the hot envelopes of the precursor objects. Runaway mergers in dense star clusters offer a third route. In clusters where relaxation times are short, massive stars can fall to the center and collide, building very large stars that end as heavier remnants. Repeated mergers among black holes in such cores can then raise the central mass further. Gravitational wave signals from the earliest epochs would be the most direct confirmation of this route. a promise held by future detectors tuned to millihertz bands. Until such listening begins, indirect signs must suffice. Compact starburst regions with extraordinary central densities and unusual kinematics would support the feasibility of this channel. Observations of winds and outflows test how engines influence their hosts. Blue shifted absorption lines from metals point to gas, pushed outward at hundreds to thousands of kilometers per second. The momentum carried by these winds can heat halos, quench star formation, or at least reshape where stars are born. At early times, such feedback may be both destructive and creative, clearing paths for ionizing photons to escape while compressing nearby clouds that then collapse into new stars. The scale of the balance depends on geometry, density, and the duty cycle of activity. If bursts are brief but frequent, the interstellar medium can remain in a churned, porous state that is efficient at letting hard radiation leak into the wider medium. Variability is another thread. Accretion flickers as disks reorganize, as clumps of gas tumble inward, and as turbulence shifts energy between layers. Even slight changes in brightness over months can betray an active nucleus when compared across visits. The cadence of early surveys is not optimized for long-term monitoring, but parallel fields and repeat observations accumulate a primitive light curve for fortunate sources. A systematic rise or drop, consistent across filters where the nucleus dominates, marks an engine. Stars can vary, but populations of stars vary collectively in ways that are gentler and slower. X-rays would clinch many cases, yet sensitivity at those energies lags at great distance. Stacking analysis across many candidates can reveal a faint average signal, suggesting that a fraction host obscured nuclei. Obscuration is expected. Dust and gas in compact cores readily hide hard engines from direct view, leaving only reprocessed light and line ratios to tell the story. Mid-infrared excesses help identify such buried sources, and their statistics constrain how many engines might be present without obvious signatures in the ultraviolet. If a hidden population is large, then accretion could have contributed significantly to the ionizing budget, even if the brightest quasars were rare. Gravitational lensing helps again by magnifying the tiniest hosts. A single nucleus can be stretched into a detectable pair of images, their small separation mapping the lens. Time delays between images at these distances are usually short, yet in principle they can be measured if variability is strong and the cadence is kind. More importantly, lens models allow reconstructions of intrinsic sizes. Some nuclei sit in hosts barely a kiloparsec across, with stellar bodies that appear adolescent while their central masses seem precocious. This compactness matches the idea that inflow streams were narrow and that angular momentum was shed quickly. Co-evolution is the long conversation that these engines initiate. In later epochs, a tight correlation links black hole mass to the velocity dispersion of the stars in a galactic bulge. If a similar relation existed in youth, it would imply a feedback loop already in place, regulating growth of both components together. The scatter in early measurements can be large because dynamical information is scarce, but hints of alignment appear when line widths and structural measurements are considered in aggregate. If alignment strengthens with better data, the engines will have to be written into the earliest chapter of galactic self-regulation. The contribution of accretion to the clearing of the intergalactic medium remains contested. On a per-object basis, a bright nucleus emits many high-energy photons. On a population basis, the rarity of such objects reduces their total share. Obscured nuclei complicate the sum. A conservative picture gives galaxies the primary role and assigns engines a supporting one. A more adventurous picture allows buried nuclei to share the work more equally. Line ratios, infrared colors, and weak X-ray stacks will continue to swing the weight between these pictures as larger samples settle the statistics. Numbers eventually return to the central tension. To light a nucleus at such distances with such brightness requires either heavy seeds, aggressive feeding, or both. The universe provides filaments of cold gas that can fuel the demand. The challenge is transport. Torques must drain angular momentum, perhaps in bars within bars, or in clumpy disks where dynamical friction drags heavy knots inward. Gas that reaches the inner parsec must survive its own radiation and wins long enough to cross the point of no return. When it does, a fraction of its rest mass turns into light with lethal efficiency. That light paints the sky with a small, distant beacon that the detectors register with satisfaction. Monsters at morning's edge do not roar, they hum. The hum is a continuum with teeth of lines, a slope in the infrared, a hard whisper hidden in possible X-rays, a soft halo of heated dust, and a faint wind pressing against the dark. Each sign says the same thing. A compact engine is awake, feeding, and altering its world. The light that arrives today began as energy ripped from the inward fall of gas by gravity's cunning. It traveled across an expanding sea to announce an early mastery of accretion. The presence of such mastery so soon reshapes questions about how galaxies assemble and how the first clearings in the cosmic fog were carved. It makes the dawn feel crowded, not by stars alone but by hearts heavy enough to bend the day around them. Creation began with simple chemistry. Clouds of hydrogen and helium fell together inside dark halos. 1,000,000 times the mass of the Sunday cooling was the gatekeeper. With no metals to radiate heat away, the gas relied on fragile molecules of hydrogen to shed energy. Those molecules formed on free electrons left by ancient ionization and on protons that met and briefly bonded. The process was inefficient, yet persistent. When enough cooling occurred, the densest knots lost pressure support and began to collapse. Gravity won the argument, and the first stars kindled. These pioneers are called metal-free because they were built from unseasoned matter. Without heavy elements, the gas could not fragment into many small pieces as easily as modern clouds do. The result favored larger clumps. Theory sketches them as giants, often tens to hundreds of solar masses, sometimes more. Their cores burned fast. Radiation flooded outward with a spectral hardness that would blister nearby gas. Their lives were measured in millions of years rather than billions. Each one was a flare rather than a lantern, but the flares were so numerous that night, learned a new color. Hints of their presence come from light, without fingerprints. A typical star-forming region shows lines from oxygen, carbon, nitrogen, and neon, the marks of processed material. A metal-free region lacks those marks. Instead, a helium line appears that demands extreme temperatures. The surrounding continuum tilts blue and stays blue even when accounting for dust. When a spectrograph captures that combination, suspicion grows that the radiation field is unusually hot and pristine. Confirmation requires exquisite sensitivity, because the galaxies that host such stars are small and distant, yet the signatures are sphinx-like rather than mute. They ask questions with enough structure to be answered. Another path to the first stars winds through their deaths. Certain masses end in pair instability supernovae. In those events, intense gamma rays in the core create electron-positron pairs, softening the pressure and causing runaway collapse that ignites explosive fusion. The star is ripped apart completely. The ejecta carry a distinct pattern of elements and a shocking brightness. At great distance, such an explosion would appear as a slowly evolving transient with colors shifting as the fireball expands and cools. Surveys can catch such events in time series if cadence and depth align. The absence of a compact remnant is the finality of this route. A heavy black hole would not form. The environment would be seeded with a characteristic mix of oxygen, magnesium, silicon, and iron that later stars could inherit. Fossils in the local universe hold whispers of that inheritance. A handful of ancient stars in the Milky Way halo carry extremely low metal content. Their atmospheres preserve ratios of elements that match the yields of early supernova models. Some show large carbon enhancements with suppressed iron, a clue to mixing and fallback in the explosions that preceded them. These chemical fingerprints are archives on stellar surfaces. They imply a generation of progenitors that never left direct descendants to be seen, only compositions for others to display. The connection between those fossils and the distant galaxies where metal-free stars would have lived remains indirect, yet it guides the interpretation of faint spectra at high redshift. Radiative feedback from the first giants was severe. Ultraviolet photons ionized their cradles and carved bubbles whose edges glowed in recombination lines. The same radiation dissociated molecular hydrogen in neighboring halos, by knocking apart the fragile bonds that cooling depended on. This created a patchwork where star formation advanced in some regions and was delayed in others. The sum over the sky produced a gradual brightening rather than a single ignition. Hard photons from hot stars also escaped into the wider medium, pressing the universe toward transparency. The synergy between starbirth, radiation, and the growth of ionized zones shaped the timeline of dawn. Magnetic fields and turbulence played quieter but decisive roles. Even a weak seed field can be amplified by folding and twisting as gas swirls inward. Magnetic tension channels flows and can extract angular momentum, allowing collapse to reach the core more efficiently. Turbulence seeds density fluctuations that either hinder or help fragmentation depending on scale. Simulations that resolve the interplay predict a range of initial masses rather than a single giant. Some fragments reach solar scale. Others grow enormous by accreting from their envelopes. Rotation complicates the picture by flattening infall into disks where gravitational instabilities create spiral waves that transport momentum. In such disks, clumps can migrate, join, or be torn apart. The outcome is a spectrum of stars that trends heavy, but is not monolithic. Observationally, candidates for extremely low metallicity populations appear as compact sources with very blue ultraviolet slopes and weak metal lines. A helium line at a particular near-infrared wavelength stands taller than expected if temperatures exceed those in ordinary starbursts. Ratios among faint lines tighten the case. Balmer lines trace the ionized gas and can show broad wings from outflows driven by intense radiation pressure. Some targets sit behind gravitational lenses, magnified into reach. Detailed modeling of their spectral energy distributions allows limits on metallicity that approach the threshold of pristine conditions. A purely metal-free population remains elusive, but examples with 1,000th of the Sun's heavy element content are within grasp, and these would be only a step beyond metal-free in their physics. The interplay between early stars and black hole seeds is intimate. Massive stars collapse into remnants when their masses fall below the pair instability window. Those remnants may be the first black holes. In dense clusters, their orbits decay, collisions occur, and repeated mergers climb the mass ladder. Gas inflowing along filaments finds these centers and feeds them, while their radiation competes with starlight in regulating the host. The chemical aftermath of each stellar death sets future cooling rates and fragmentation scales, closing a loop between generations. The first stars, therefore, began a conversation across time, speaking through light while alive, and through chemistry after death. Dust arrives earlier than caution, predicted if the stars are massive and brief. Supernova ejecta condense grains in cooling tails. Those grains absorb ultraviolet radiation and re-emit in the infrared, altering spectra and enabling new cooling channels in subsequent clouds. With dust present, smaller fragments can collapse. The initial mass function tilts toward lower masses, and long-lived stars begin to populate galaxies. This threshold marked a shift from extraordinary to ordinary star formation. The presence or absence of dust features in faint high redshift spectra locates that shift on the calendar. Signals that cannot be seen in starlight alone offer corroboration. At radio wavelengths, neutral hydrogen in vast regions resonates and leaves a faint background that depends on the temperature of the gas and the illumination by early radiation. Spatial structure in this background is shaped by the clustering of the first light sources. Maps in development aim to turn these resonances into three-dimensional charts of dawn. When such charts are paired with deep infrared images, the placement of star-forming regions within the evolving fog can be measured directly. It is cartography at the edge of visibility. The environment around each early halo matters. Filaments deliver cold gas in streams. Mini-mergers bring fresh fuel and perturb disks, triggering bursts. Strong tidal fields tear at nascent structures and rearrange angular momentum. The local Lyman-Werner radiation field sets whether neighboring halos can cool or must wait. In rare locations where the field is intense and synchronized, the path to a monolithic collapse that forms a heavy black hole seed opens. In more common settings, small clusters of metal-free stars flare and expire, leaving pockets of enrichment that lace the next wave of clouds with new physics. A single metal-free star is beyond direct resolution at such distances. The signature lies in ensembles. If galaxies dominated by these pioneers are common at specific redshifts, their combined light shapes the luminosity function, steepening the faint end. Their hard spectra elevate certain helium lines above expectations. Their lack of metal lines tightens upper limits on oxygen and carbon. Their deaths raise the rate of exotic supernovae and alter the distribution of element ratios in later generations. Each of these knobs can be turned by measurement until a consistent set of positions aligns with theory. The birth of the first stars is not just a fact. It is an origin of origins. Heavy elements that will one day compose planets and bones were minted in their cores and their explosions. Photons that will one day pass through mirrors were born in the fires those elements enable. The timeline of reionization reacts to how quickly such giants appeared and how generously their light escaped. The character of early black holes reacts to how the giants ended. The modes of star formation seen in later epochs react to the threshold when dust and metals tip the balance toward fragmentation. To read the signatures of these beginnings is to watch necessity turn into variety. The sky, patient and vast, carries the traces. The method is to collect them with steadiness, to compare the faintest lines against predictions born of gas dynamics and nuclear physics, and to honor both success and discrepancy. If a truly pristine population is found, it will be small, brief, and decisive. If only nearly pristine examples appear, they will still instruct, defining the slope on the road from simplicity to complexity. The first stars are not gone. Their influence resides in every spectrum and in every atom heavier than helium. Their light was the first handwriting on the darkness, and the letters have not faded. Matter learned to braid itself. Gravity pulled on tiny fluctuations left by an early whisper and stretched them into filaments that crossed the young cosmos like faint riverbeds. Between the filaments lay voids, hollows that grew emptier as their boundaries thickened. Where threads met, knots formed. Those knots became the earliest cities of stars. The pattern was not a smooth glow, but a lattice, clumpy and uneven, a scaffold on which light could hang. A deep image reveals this when the faintest structures are allowed to speak. Tiny galaxies collect along invisible lines. Pairs and triplets align more often than chance. Redshifts peel the picture into layers, and the layers trace strands. Simulations prepared the expectation. Start with a sea of dark matter and let it move under its own gravity. It collapses first along one axis, becoming a sheet, then along a second, becoming a filament, and then at crossings into halos. Gas follows, slowed by shocks and heated by compression, yet always seeking the same caustics where density concentrates. By itself, this story writes geometry. Add cooling, turbulence, and radiation, and the geometry begins to shine. Observations pull the geometry back out of the glow by using statistics instead of outlines. Counts of neighbors as a function of distance reveal clustering. The correlation function rises at small scales, drops, and rises subtly again, its shape encoding the typical halo masses that host galaxies. Even at extreme redshift, the curve refuses to flatten. Galaxies were never alone. A field at high magnification sharpens the message. Lensed arcs unveil composites of clumps only a few hundred parsecs across. Chains of knots point along a direction like beads on a string. Their colors match within narrow limits, suggesting synchronized bursts triggered by a common inflow. Another field without a lens but with patient exposure shows an overdensity in redshift space, several galaxies within a small velocity window. That window corresponds to a co-moving slice of space, where a filament axis points along the line of sight. The impression is of a budding cluster, a region destined to grow into a massive node given time. Such protoclusters are rare but instructive, offering a glimpse of hierarchy already underway. Kinematics add depth. A slit placed across a compact galaxy returns a line tilted by rotation or muddled by turbulence. The tilt is often modest, the dispersion is often large. Inflows along filaments deliver gas with misaligned angular momentum, building thick, unstable disks where gravity fights pressure on short times. The Toomre parameter, a measure of stability, dips below unity and fragmentation follows. Clumps form, migrate inward under dynamical friction, and sometimes merge at the center, feeding a bulge or a seed that waits there. Outflows from supernovae and young stars blow cavities, perforating the disk and lowering the local escape threshold for hard photons. The combination imprints a clumpy morphology and a clumpy escape of radiation that contributes unevenly to the clearing of the intergalactic medium. The cosmic web does not glow in a single color. Different tracers reveal different bones. At near-infrared wavelengths, young stars mark the densest knots. At mid-infrared, warm dust outlines pockets where emission is reprocessed. At longer wavelengths, lines from ionized oxygen and carbon draw maps of cooling gas. In principle, faint ultraviolet fluorescence from hydrogen should coat the filaments, lit by the ambient radiation field. With sufficient sensitivity, wisps of this glow hint at extended halos around compact cores, suggesting reservoirs that will feed star formation for millions of years. Stacking techniques make these halos visible statistically, revealing excess light around many small systems once the average is taken. Weak gravitational lensing sketches masked directly by its gentle warping of background shapes. At great distance, the signal is faint, yet over wide fields a coherent shear pattern emerges. The pattern confirms that light follows mass imperfectly. Some bright regions sit on modest halos, some dim regions hide heavy scaffolding. Matching lensing maps to galaxy positions measures bias, the tendency for luminous matter to cluster more or less strongly than dark matter. In youth, bias is high. Galaxies occupy the rare peaks in the matter field, and those peaks are more strongly clustered than the average C. The measured bias feeds back into the translation from observed clustering to halo masses, tightening the assignment of galaxies to their hosts. Fluctuations in the intergalactic medium respond to the Webb as well. Along lines of sight to luminous sources, absorption by neutral hydrogen lays down a comb of troughs. Even when the average neutrality is low, the pattern retains memory of density contrasts, with thicker regions creating deeper notches. At earlier times, as transparency emerges patchily, the notches widen and blend into extended valleys. Cross-correlating the positions of galaxies with these features tests how ionized bubbles trace the Webb. Overdensities tend to clear first because they host more sources of light, yet overdensities also accumulate more gas. The competition between production and supply determines the shape of the patchwork. Protogroups appear as gatherings of a few galaxies in tight proximity. Their tidal interactions leave signatures in disturbed morphologies and bridges of diffuse light. These encounters are not gentle. Gas flows along bridges, triggering star formation where clouds compress. In the crowded geometry of a filament intersection, relative velocities remain low enough for mergers to occur frequently. Each merger reshuffles angular momentum, often dumping material toward the center where compact components grow. The result is not a smooth growth curve but a punctuated one, a stair of mass that rises with episodes of violent rearrangement. Power spectra of the galaxy distribution at early times carry hints beyond the simple slope. Features born of sound waves in the early plasma leave a gentle ripple at a preferred scale. Detecting this imprint at youth is difficult because volumes are small and samples sparse. Yet each step toward it adds to a consistent cosmological story in which the same physics writes across ages. The presence of the ripple, even in infancy, anchors distances and expansion without appealing to any single object's peculiarities. Gas that has not yet learned to shine directly can still be mapped through its faint millimeter lines. Mixing data from infrared images with surveys that scan for C2 or O3 emission over large fields creates an intensity map, a statistical image where individual sources blend into a background that fluctuates with environment. Peaks in these maps line up with peaks in the density of infrared-selected galaxies, confirming that the coolants trace the same scaffolding. If such maps are compared with low-frequency radio observations that trace remaining neutrality, anti-correlations appear where ionized bubbles have eaten into the fog around filaments. The chessboard of ionization then overlays the Webb like sunlight through leaves. Angular momentum transport along streams shapes what happens inside halos. Cold flows arrive in narrow tongues that pierce the outer shock and feed disks directly. At their points of impact, Rings form and fragment into clumps. Spiral arms grow in self-gravitating response, and these arms act as conveyors of momentum, allowing gas to slide inward. The balance between inflow and feedback sets the clump lifetime. If outflows are strong, clumps evaporate quickly and new ones form, keeping the pattern fresh. If outflows are moderate, clumps survive long enough to migrate and central concentrations rise. The observed range of clump sizes and contrasts suggests both regimes occur, guided by local depth of potential and by the geometry of the feeding streams. Environment affects metallicity. Galaxies in richer nodes tend to show slightly higher heavy element abundance at fixed mass than those in sparse filaments, even at early times. Recycling of outflows is faster where gravity is strong. Inflows mix with processed gas more thoroughly. The metallicity gradient within a single galaxy can be reversed under such rapid cycling, with central regions surprisingly metal-poor if fresh inflow dominates, or enriched if feedback has had time to stir and return ejecta. Integral field spectra at high redshift begin to trace these gradients, turning each compact source into a small world with weather. The Webb also modulates time. Light from sources in a dense region traverses more structure, encounters more mini-halos, and may be scattered or delayed in subtle ways. While absolute time delays are tiny on cosmic scales at these distances, the cumulative scattering alters the statistical relationship between line-equivalent widths and continuum slopes. Such systematics, once modeled, refine the use of emission lines as clocks and mass gauges. Precision emerges from acknowledging the Webb rather than pretending a uniform ocean. A clumpy dawn changes expectations about the pace of transparency. If most star formation perches on filaments and nodes, then the earliest clearings will form around those same places. Voids will lag, remaining neutral longer. The topology of reionization becomes sponge-like rather than bubble-like, with channels opening along strands before cavities widen elsewhere. Measurements that count line emitters as a function of environment test this topology. A deficit of emitters in underdense regions at a fixed redshift signals residual fog, while an excess in overdense regions betrays advanced clearing. The pattern that emerges is consistent with light choosing the already prepared paths first. Nothing in this web is static. Filaments thicken as matter streams along them. Nodes grow by ingesting neighbors. Voids relax into gentler gradients. Within the threads, galaxies live brief luminous lives, flickering as they accrete, burst, and quench in cycles set by the fuel lines that feed them. The portrait is one of motion disguised as structure. Even the smallest clump is a process in progress, a balance between collapse and disruption, between inflow and feedback, between cooling and the heat poured back by its own newborn stars. The clumpy web at dawn is therefore both map and mechanism. It tells where the first energy was spent and how matter arranged itself to harvest gravity most efficiently. It frames the stage on which small galaxies multiplied and on which the earliest giants learned to assemble. It directs streams, modulates chemistry, and edits the escape of the light that made space transparent. In recognizing the pattern, a narrative takes form that does not seek smoothness. It seeks the grain of reality, the way a universe builds itself from threads pulled taut across a very young sky. Grains rise where fire has barely cooled. Tiny solids condense out of gas that only recently knew the pressure of a stellar heart. Each grain is a record of temperature, density, and chemistry. At the moment it froze from vapor into mineral. Carbon arranges into soot-like cages and sheets. Silicates knit oxygen with magnesium and silicon. Iron condenses as metal or oxide. These are not pebbles, they are specks, submicron travelers that change how light moves and how gas cools. Their presence in the earliest galaxies announces that heavy elements were minted and assembled with surprising haste. The first factories are violent. Massive stars burn quick, fuse to iron, and fail as supernovae. In their cooling ejecta, molecules form and seeds grow. The mass of dust per explosion depends on mixing and on the density of the material that flows back inward as a reverse shock. Some grains shatter, others survive and enter the interstellar sea. The tally from a population of such deaths can be large enough to explain early redness in spectra and significant opacity in ultraviolet bands. A quieter factory arrives later in the lives of intermediate mass stars. When their envelopes swell and cool, carbon and oxygen combine into solids that drift away in winds. That path, though efficient, requires longer times than the youngest systems allow. The balance implies that supernovae begin the job and that growth in dense clouds completes it. Growth after birth is the secret accelerator. In cold molecular gas, atoms and small molecules stick to grain surfaces and rearrange into mantles. Carbonaceous mantles thicken, silicate lattices repair. The rate depends on density, temperature, and the availability of metals in the gas phase. Depletion patterns measured from faint lines show that certain elements vanish from the gas, locked into solids. The dust-to-metal ratio then climbs toward values that would be expected only in more mature galaxies. Such ratios argue for rapid cycling of gas through phases where grains can grow and be protected from shocks. The presence of dust changes the script for star formation. Radiation is absorbed and re-emitted at longer wavelengths, cooling the surroundings and shading pockets that might otherwise be stripped by starlight. Gas can then fragment into smaller clumps, enabling low-mass stars to form. A threshold in dust abundance marks the transition from a mode dominated by massive pioneers to a mode that populates the main sequence of long-lived stars. That threshold is crossed abruptly if enrichment is rapid and clouds are dense. The effect is not only thermal. Dust catalyzes chemistry by providing surfaces where molecules assemble. Hydrogen finds partners more easily on grains, oxygen couples to form water, and carbon chains lengthen. The molecular richness of a cloud sets the cooling curve and the pace of collapse. Light passing through dusty gas carries the imprint of grain size and composition. Blue wavelengths are scattered and absorbed more strongly than red, reddening the continuum. The detailed shape of that reddening curve varies with the mixture of grains. In systems with low metallicity, a steep curve is common, reminiscent of the pattern seen in small neighboring galaxies where dust is simple and lacks the prominent bump found near a specific ultraviolet wavelength in richer environments. Measurements of the relation between infrared excess and ultraviolet slope test how efficiently dust reprocesses radiation. Early points on this diagram sometimes fall below the trend established later, implying warmer dust or different geometry. Clumpy arrangements allow light to escape through holes, while other paths are thick with grains, complicating a single prescription. Warmth is the other signature. Grains re-emit in the infrared, with temperatures governed by the intensity of the local radiation field and by their sizes. In young starbursts, the field is fierce, and small grains heat to tens of kelvins above the cosmic background. Their glow peaks at far infrared wavelengths that shift into the millimeter range with distance. Mapping this glow turns the hidden half of star formation into numbers. Flux becomes dust mass when a temperature is assumed, tempered by the emissivity of the material. Temperatures tend to run high in compact systems, lowering the inferred masses for a given luminosity. That bias must be weighed carefully, as it can mask a large reservoir of solids if the chosen temperature is too warm. Lines from ionized and neutral species complement the continuum. A fine structure line of singly ionized carbon shines brightly in photodissociation regions where ultraviolet light grazes molecular clouds. The line traces the borderlands between hot and cold. Another line from doubly ionized oxygen arises in zones lit by very hard radiation. The ratio of these lines to the infrared continuum calibrates the efficiency of star formation and the density of gas. Spatially resolved measurements in fortunate lensed galaxies reveal clumps of emission offset from the stars, evidence of feedback carving channels and of fresh inflow striking disks. Such maps tie the dust to its makers and show how grains ride winds or settle in lanes fed by filaments. Polycyclic aromatic hydrocarbons introduce their own chorus. These molecules vibrate and glow in mid-infrared bands when bathed in ultraviolet light. Their presence signals a certain maturity of chemistry and a resilience against destruction. In metal-poor environments, they are fragile and often suppressed. When their features begin to rise in distant galaxies, they mark a turning point where carbon chemistry has established itself strongly enough to survive the glare of young clusters. The pattern of their strengths relative to the continuum and to ionic lines constrains the spectrum of illuminating stars and the hardness of the local field. Dust is both veil and archive. It hides young stars at short wavelengths, then returns their power shifted into a redder, softer language. It also records the history of enrichment through its composition. Ratios of crystalline to amorphous silicates, of graphite-like to aliphatic carbon, and of iron inclusions are difficult to measure at great distances, yet even crude inferences place footholds on a timeline of mineralogy. Early signs often point to amorphous dominance, consistent with rapid condensation and limited annealing. Over time, shocks and heating alter the mixture, but in youth, the imprint of swift creation should be strong. The impact on cosmic transparency is double-edged. Grains absorb the same photons that would ionize hydrogen. In dusty regions, fewer escape into the wider medium. At the same time, feedback that stirs and punches holes in the interstellar medium can funnel light out efficiently along clear channels. The net effect depends on architecture. A porous, clumpy arrangement with modest overall dust mass can transmit a healthy fraction. A uniform thick layer can smother. Observations that compare the strength of hydrogen recombination lines to the ultraviolet continuum constrain the escape, while the infrared luminosity measures how much light has been trapped and re-radiated. Together, these gauges set the contribution of each galaxy to the clearing of the fog. Fast enrichment at youth nudges models toward fuel lines that are steady, and toward star formation that is intense, but not immediately self-defeating. If outflows carry metals far, dust seeds larger volumes and accelerates cooling widely. If outflows stall and fall back, enrichment localizes and drives rapid internal change. Either path supports early dust, but the resulting distributions differ. Extended halos of faint infrared emission would argue for widespread seeding. Compact cores with bright continuum would argue for concentration. Deeper integrations continue to stretch toward these halos, balancing against the challenge of surface brightness dimming. Quasars in the distant universe present extreme cases. Their hosts can harbor enormous dust masses, implying either exceptional yields per event, rapid grain growth, or both. The engines at their centers flood their surroundings with hard light that should erode small grains. Yet dust survives in copious amounts, perhaps sheltered in dense clumps or replenished constantly. The contrast between such hosts and the more common small galaxies underscores the variety of environments that developed quickly. It also cautions against a single narrative for dust production. Multiple channels likely operated side by side, their relative weight set by local density, star formation history, and the presence of an active nucleus. Foreground screens complicate interpretation. Light from ancient galaxies threads its way past nearer dust that sits in our own neighborhood or in intervening systems. Careful modeling subtracts these contributions, but uncertainties remain largest at the longest wavelengths where diffuse emission rises. Cross-checks with blank fields and with regions at different ecliptic latitudes reduce the risk. In the end, the grains that matter for the story are those bound to the galaxies under study, the ones that carry the memory of their host's brief but fiery youth. Grains born early are not passive debris. They are instruments of change, adjusting temperature, catalyzing molecule formation, shaping the spectrum, and storing the record of how quickly matter turned from simplicity to structure. Their survival through shocks testifies to quiet corners where turbulence rests, and to rapid cycles that grow them back after damage. Their extinction curves sketch their sizes. Their infrared glow counts their abundance. Their features whisper their chemistry. Taken together, they confirm that complexity arrived swiftly, that the first furnaces did more than light the sky, and that the materials for worlds were assembled in time to matter. Light does not travel a straight road. It moves through a geometry that curves wherever mass gathers and stretches wherever space itself expands. Every ancient photon is both a messenger and a map. Its color shifts as the scale of the universe widens. Its path bends where clusters of galaxies weigh on space-time. Its rhythm slows when clocks are carried to distant epochs. A telescope that listens in the infrared receives these relativistic signatures not as abstractions but as practical tools. With them, the young cosmos can be measured with geometry rather than guesses. The red of great distance is the first signature. A wavelength launched in ultraviolet arrives in longer color because the scale factor has grown while the photon traveled. That growth divides its energy by the same factor and counts years by how much the spectrum moved. In a plot of flux against wavelength, familiar lines slide into new positions. The amount of slide defines redshift, and redshift becomes distance without needing a ruler made by human hands. This is cosmological redshift, born from expansion itself, not from motion through space. It tells that the messenger crossed an ocean that was swelling even as it sailed, and that time at the source was earlier in the book than time at the detector. Dimness adds another imprint. Surface brightness fades by a power of 4 in 1 plus redshift. 2 parts come from simple geometry. 1 part comes from the loss of photon energy to stretching. 1 part comes from the longer arrival interval between successive wave crests. Dimness is therefore a compound of distance and time dilation. A distant galaxy appears not only fainter, but intrinsically quieter per unit area. The penalty is severe, yet the measurement becomes a confirmation of relativistic accounting. When stacked images rise above noise, the recovered structure follows the expected law. Brightness falls in exactly the way expansion demands. Curvature writes the next script. Massive clusters of galaxies sit like mountains in space-time. Light from still more distant sources flows around those mountains, and the geodesics are not straight in Euclidean sense. Multiple images of the same background object appear at positions set by the mass in the lens and by the distances between observer, lens, and source. In deep images, these repeats are common as arcs and counter-arcs. Their shapes encircle an invisible radius known to theory as an Einstein scale. By tracing that curve precisely, the unseen mass distribution within the cluster can be reconstructed without asking whether it glows. Dark matter comes into view through its bend rather than through its light. Time delay is the subtle twin of bending. 2 images of the same source do not arrive together. One path is longer. One path passes through deeper potential. The difference produces a measurable offset in arrival time when the source changes brightness. Transients provide the clock. A supernova flares in one image and later in another. The offset depends on the gravitational potential along each route and on the expansion rate that stretches the routes. Measuring both the geometry and the delay turns space-time into an instrument for cosmology. The method is sensitive to how quickly the scale factor grows, and therefore to the energy budget of the universe. In a young epoch, the same principle applies. Delays that are days or weeks become cosmological rulers drawn by gravity itself. Microlensing adds texture on top of the grand curve. Individual stars in a lensing galaxy act like droplets on a curved sheet of glass. As the background object and the lens move relative to each other, tiny caustic networks sweep across the source. Brightness flickers on scales of days to months. In high-resolution images, knots within lensed arcs sparkle differently at different times. From that twinkling, the scale of emitting regions can be inferred. Star-forming clumps, accretion disks, and diffuse halos respond with distinct amplitudes. This is relativity brought to the level of substructure. The bending of light, by stars that the eye will never resolve, becomes a microscope for components that the eye would never separate. Weak lensing paints on even larger canvases. It does not create dramatic arcs, but a coherent shear in the shapes of many background galaxies. Statistical alignment reveals a field of gentle distortions that reflect the mass distribution over wide regions. At early times, the signal is small and patience is required. Yet by weaving together many fields, a low-level pattern emerges that checks how structure grew under gravity governed by general relativity. The result supports a picture in which light traces matter, with a bias that depends on halo mass and epoch. The shape of the shear spectrum becomes one more test that curved space-time explains the observed clustering. Relativity also slows the beat of events. A supernova in a distant galaxy rises and fades, with a light curve stretched by 1 plus redshift. A transient's timescale measured in the observer's frame is longer than in the rest frame by exactly the expected factor. This time dilation is not an optional detail. It is proof that cosmic expansion affects clocks as well as colors. When a series of visits catches a high redshift explosion, its cadence verifies the prediction. When a dusty core flickers, the spectral changes follow the slowed clock. The alignment of theory and observation at these faint levels is a quiet triumph of the same equations that make black holes inevitable and gravitational waves real. Kinematics inside young galaxies speak to gravity's script. Rotating clumps exhibit velocity gradients across slits and integral field units that can be modeled with disks, turbulence, and inflow. The amount of velocity that can be held by a given amount of light demands dark halos whose shapes and concentrations compare with those expected from cold, dark matter. The match is not perfect in each case, but in ensemble it upholds a consistent curve that runs from compact systems at youth to large spirals later. Relativistic gravity is the backdrop. Newtonian approximations suffice within small fields, yet the larger framework assigns distances and sets the relation between measured redshift and physical scale. Angular diameter distance behaves in a way that feels counterintuitive yet belongs to curved spacetime. As redshift increases, apparent size at fixed physical scale first shrinks and then grows. Objects at very high redshift can look larger on the sky than similar objects at intermediate distance. This turning point arises from the geometry of an expanding universe with a non-zero cosmological constant. When small galaxies at extreme redshift are measured, their sizes versus redshift follow the predicted curve once lensing magnification is accounted for. The observed trend is a geometric conformation hiding inside a catalogue of morphologies. Relativity threads into chemical clocks as well. Radiation from hot stars and accretion disks ionizes gas, and the resulting line ratios depend on density, temperature, and the intensity of the field. Those properties are shaped by the depth of gravitational potential wells that define escape speeds and turbulent support. At early times, the measured line widths sometimes exceed the rotational support expected from the compact sizes and inferred masses. The surplus is turbulence driven by rapid accretion and feedback, yet the baseline remains gravity's well. Modeling these profiles yields dynamical masses that can be compared to stellar masses derived from spectra. Where discrepancies appear, lensing corrections and inclination often cure them. The language of curved spacetime remains the dictionary for translating light into matter. Foreground clusters provide laboratories for testing the microphysics of gravity's arc. Flux ratios among multiple images can disagree with smooth lens models. The anomalies point to subhalos of dark matter that granulate the potential. Counting such anomalies constrains the small-scale power spectrum and therefore the temperature and interactions of dark matter. General relativity supplies the lensing formulae. The number and mass of the clumps provide the physics to be tested. In high-fidelity images, the anomalies swing the debate between cold, warm, and self-interacting flavors. Even at early epochs, the presence of substructure in lenses at lower redshift echoes across the analysis of distant arcs. Cosmic chronometers live inside the spectra as well. The age of a stellar population at a given redshift constrains how long there has been to build it. When those ages press against the cosmic time allowed by the expansion history, tension appears that can be relieved by revising star formation histories, dust assumptions, or lensing magnifications. If tension persists, it might ask whether the expansion rate is exactly as other probes claim. The answer so far is that careful accounting brings harmony. Relativity's clock and the population's clock differ only when uncertainties are wide. With better data, the two clocks agree. Polarization provides another route. Scattering in asymmetric outflows and disks introduces a preferred orientation in light. In lensed systems, differential magnification alters the polarization pattern across images. Comparing these patterns to lens models adds constraints on geometry and on the relative contribution of stars and engines to illumination. The physics remains classical in the scattering, but relativistic in the way rays are bent toward the detector. Every extra constraint tightens the reconstruction of sources that no direct resolution could achieve. Relativity in a young universe is not a special case. It is the full theory applied where it first mattered. Curvature makes lenses of clusters. Expansion reddens and slows light. Time delays turn variability into rulers. Weak shear lines up galaxies across fields no chart had connected. Dimness follows a law fixed by energy, area, and cadence. Each of these is measured with cold detectors and long patience. Each returns values that slot into a consistent cosmic story where gravity is geometry and light is obedient to its shape. The youngest structures therefore confirm the oldest equations. They do so while offering refinements that sharpen knowledge of dark matter's granularity, of the growth rate of structure, and of the expansion history that sets the relation between color and clock. The curvature of space-time is not a decoration on the images. It is the canvas on which the images exist. To see the dawn is to see geometry itself acting on light, turning distance into hue, mass into arcs, and time into a softened rhythm that reaches the present with quiet authority. Competing plans for the first morning gather like architects around a table, each unrolling a drawing that could explain why youth looks so accomplished. The blueprints share foundations in gravity and thermodynamics, yet their upper stories differ. Some widen the stairways of starbirth, some enlarge the engines at galactic hearts, some rearrange the material that darkens the blueprint itself. Together they form a catalogue of possibilities to be weighed against spectra and shapes that have travelled an expanding sea. One plan redraws how clouds fragment. In gas with few heavy elements, cooling stalls at higher temperatures, pressure remains stronger, Jeans masses rise. The initial distribution of stellar masses tilts toward heavy stars. A top-heavy population radiates more per unit mass, so the same light demands less built material. Short-lived giants then enrich their surroundings fast, enabling smaller fragments in the next cycle. The blueprint predicts blue continua, strong helium lines, and rapid chemical change measured by faint oxygen and carbon features that grow from invisibility toward modest strength in brief spans of cosmic time. A second plan enlarges the nuclei early. Black hole seeds begin heavy rather than humble. In halos drenched by a strong Lyman-Werner radiation field, molecular hydrogen is broken, preventing efficient fragmentation. Gas collapses nearly isothermally into a supermassive star or quasi-star that soon fails into a black hole with a mass far above ordinary remnants. These seeds then accrete at comfortable rates to reach observed weights. The signatures would be compact hosts with very hard line ratios, mid-infrared excess from heated dust, and kinematics that reveal high central dispersions in galaxies otherwise small and young. A third plan keeps the seeds modest but feeds them aggressively. Accretion exceeds the standard radiative balance in thick, radiation-trapped flows. Slim disks develop funnels that vent light, while mass streams continue inward. Duty cycles are high, flickering but persistent. Where geometry allows, Super Eddington episodes stack into swift growth. Observables include broad but sometimes muted lines from partially obscured cores, variability at rest frame weeks to months, and winds whose momentum rivals or exceeds that available from simple starlight. A fourth plan changes the roads that fuel travels. Cold filaments deliver gas deep into halos, bypassing hot buffers that would otherwise stall inflow. Angular momentum is bled away by spiral waves and clump torques in thick disks. Bars within bars form transiently, passing momentum outward and mass inward toward a center primed for star formation and accretion. Predictions here are rotationally modest, but dispersion, rich kinematics, chain-like morphologies of clumps along preferred directions, and rapid migration of those clumps to central concentrations within a few dynamical times. Another plan redraws the matter that does not shine. If dark matter is not perfectly cold and collisionless, the small-scale scaffolding shifts. Warm varieties erase the tiniest halos, pushing growth into larger seeds that more naturally host luminous bursts. Self-interacting varieties scatter in dense cores, flattening central cusps and changing merger histories. Observational checks come from counts of faint satellites in later epochs, lensing anomalies that betray subhalo populations and the clustering bias of early galaxies. Any viable alteration must match large-scale structure while solving small-scale tensions without inventing new ones. A rival plan leaves dark matter untouched, but adds a small early energy component. Early dark energy injects pressure near recombination or slightly later, temporarily changing the expansion rate. Distances at fixed redshift shift subtly, altering inferred luminosities and volumes. Structures grow under a slightly different calendar. If tuned carefully, this component could ease discrepancies between measured ages of luminous young systems and the time available to build them. Tests appear in background radiation patterns, in baryon-acoustic feature positions, and in distances to standardizable candles at intermediate redshift. Yet another plan nudges the statistics of the initial ripples that seeded structure. Non-Gaussianity at a low level can raise the odds of rare peaks without dramatically altering the broad field. More early peaks mean more heavy halos available for luminous bursts. The imprint of such a change is a distinctive scale-dependent bias in clustering. On large scales, galaxy positions would depart from the expectations of purely Gaussian beginnings. With larger samples, the bias can be charted, and the allowed non-Gaussianity squeezed into or out of relevance. Some blueprints emphasize radiation backgrounds as regulators. A strong near-ultraviolet field can suppress cooling in small halos, delaying first stars locally while enabling direct collapse in special places. A background of X-rays from compact objects preheats the intergalactic medium, easing the path for ionization, but altering the contrast of emission lines. The relative timing of these backgrounds shapes when and where the fog thins. Observable consequences include the equivalent widths of key lines, the prevalence of hard ionization features, and the cross-correlation between galaxy positions and maps of neutral gas at long wavelengths. Feedback prescriptions compete as well. One design makes supernovae and stellar winds punch clean holes through disks, raising the escape fraction of ionizing photons while keeping enough gas bound to sustain bursts. Another makes those same agents expel gas so thoroughly that growth pauses between episodes, lowering the long-term star formation efficiency but allowing dramatic short-term flares. Engines at galactic centers add their own pressure, sometimes carving cones of clarity, sometimes cloaking regions in dust. The balance these forces strike determines not only brightness, but the topology of transparency around each source. Dust chemistry supplies a late-arriving but potent lever. If grains grow quickly in dense clouds, cooling accelerates and fragmentation proceeds to low-mass stars, lowering light per mass and lengthening the average stellar lifetime. If grains are scarce or easily shattered, massive stars dominate longer, boosting ultraviolet output and making spectra harder. Infrared excess at fixed ultraviolet slope, the emergence of specific mid-infrared bands, and far-infrared continuum temperatures all serve as diagnostics for which lever is being pulled. A conservative plan insists that the universe behaves as modeled and that anomalies are artifacts of measurement. Photometric redshifts can be fooled by extreme emission lines at lower distance. Stellar masses can be overstated if nebular continuum and lines fill filters used to measure starlight, or if assumed star formation histories are too smooth. Lensing magnifications can be misestimated, pushing objects too high on luminosity scales. Surface brightness selection can bias samples toward compact, intense phases while missing extended, dim components. This blueprint demands deeper spectra, multiple instruments, and independent reductions to pair uncertainties until tensions recede. Assembly bias outlines another path. Halos of the same mass grow differently depending on their larger environment. Those that formed earlier can host galaxies with higher concentrations and altered star formation histories. In an infant universe where cosmic time is short, such differences matter greatly. If surveys happen to sample regions where assembly skewed early, the picture can look precocious without violating global averages. Clustering measurements that separate by mass proxies and redshift sharpen whether environment alone can shoulder the load. Bursty star formation histories form a more human-scaled plan. Young galaxies flicker. A brief episode of intense ignition can lift a system across a detection threshold, inflating inferred masses if the models assume steady light. After the burst, luminosity drops rapidly. If surveys are biased toward catching those ups, counts of bright objects climb without requiring long sustained growth. The signature would be high specific star formation rates, strong nebular lines, and a mismatch between ultraviolet and infrared estimates where dust is modest. Repeated visits that catch declines would confirm the flicker. Rare structures provide still another variant. Protoclusters and dense filaments concentrate halos and gas. They act as accelerators that produce outliers. A field that lands on such a region can exaggerate brightness functions. The cure is breadth. Wider surveys average over cosmic variance and reveal whether early overachievers were local phenomena or common circumstance. If outliers persist after averaging, they demand physics. If they fade into the mean, geometry was the magician. In practice, the final plan will borrow rooms from many drawings. Top-heavy early stars can coexist with heavy seeds in a few favored halos. Cold flows can feed both clusters of giants and central engines. Dust can grow fast while feedback opens windows for light to escape. Non-Gaussian ripples can be small yet sufficient to tilt the odds toward dramatic peaks in volumes the size of current surveys. Measurement systematics can enrich or erode all of these claims depending on how rigorously they are handled. The judge is comparison at scale. Luminosity functions measured across independent fields, clustering that fixes halo masses and tests bias, line ratio diagrams that partition stars from engines, infrared to ultraviolet relations that calibrate dust, and lensing reconstructions that correct brightnesses all converge on a verdict. Each blueprint must not only match a single statistic, but a web of them. When a plan fits one and fails others, it is revised. When it fits many, it earns a place in the combined design. The rivalry is not combat, but correction. Nature allows only one history. The task is to retrieve it from faint signs. Reasonable blueprints are the scaffolds that hold thinking in place while measurements climb. When new data arrive, beams move. When a detail proves fragile, supports shift. The emerging structure is neither the most conservative nor the most radical option by default. It is the one that leaves the smallest residue of unexplained features in spectra, images, and counts. In that chosen architecture, gravity remains the engineer, cooling the interior decorator, radiation the electrician, dust the insulator, and dark matter the foundation poured long before any room caught light. Machines listen by cooling themselves into stillness. Detectors that would otherwise sing with their own heat are lowered toward the quiet of interstellar night until thermal whispers fall beneath the sound of distant galaxies. In that engineered hush, starlight lands as single charges in wells etched from semiconductors. Each well is a promise to count rather than guess. The promise is kept by arrays tiled into cameras and spectrographs, whose entire purpose is to turn faint photons into information precise enough to test ideas. An eye that images the near-infrared uses mercury-cadmium telluride grown so carefully that dislocations are rarer than the photons it seeks. Each pixel integrates current, while a readout samples the accumulation many times, fitting a slope instead of accepting a single point. Sampling up the ramp filters out cosmic ray hits that would otherwise bury a count in sudden spikes. Dithers step the field across the array by small offsets, smearing fixed pixel quirks into harmless averages. The result is a mosaic, with the scars of hardware removed and the sky's texture left intact. A second eye slips a prism or a grating into the beam and stretches the light into bands. Modes trade resolution for reach. A low dispersion prism captures an entire spectrum from the reddest visible light to the threshold where cold dust glows, the kind of overview that finds key features quickly. Higher dispersion gratings split narrower intervals finely, separating lines that would otherwise blend. Slits confine the light from a target and avoid contamination. A micro-shutter array, composed of nearly 250,000 tiny doors, selects hundreds of targets at once across a field, each door toggled by magnetic and electrostatic choreography. The pattern of open shutters is a mask written in real time, a map that tells the instrument where to listen. Another instrument breathes deeper cold through a cryocooler, to reach the longer wavelengths where dust radiates and molecules stir. Its detector is silicon doped with arsenic, tuned to notice light that ordinary semiconductors ignore. At these energies, photons feel like warmth rather than color, and the challenge is to keep the instrument colder than the signal it wants to see. Inside, an integral field unit slices the image into thin strips, disperses each, and then reassembles them into a cube whose axes are two angles on the sky and one in wavelength. Every spaxel carries a spectrum. A nebula becomes a stack of transparent layers, each layer a chemical and kinematic map. Guidance rides on a separate pair of sensors that watch modest stars with steadfast attention. Microthrusters whisper to reaction wheels and hold the observatory steady with a stubbornness that refuses to surrender arcseconds. A stable pointing is not decoration. It is the difference between a spectrum disentangled from its neighbors and a soup, between a coronagraphic image that suppresses a glare and one where the star bleeds across the field. Coronagraphs within the instruments use masks and stops to cancel starlight and reveal companions or structures otherwise lost. Algorithms then subtract the residue of that glare with reference images and principal components. What remains can be a ring of dust, a vortex carved by a forming planet, or a point where a world's glow barely escapes its parent's glare. Calibration begins in darkness. The instrument measures itself with shutters closed, building maps of dark current and persistence. Lamps feed lines of known wavelength into the optical train to verify dispersion and to anchor the relation between pixel and color. Flat fields, created by uniform illumination, find subtle variations in sensitivity across the arrays. A cycle of observations on empty sky tests backgrounds and drifts. The discipline resembles tuning a musical instrument by identifying every fret and listening for buzz before the performance begins. Once tuned, the machine still requires constant attention. Temperature swings, small hits from micrometeoroids, and memory effects leave tiny fingerprints that must be recognized and removed. Pipelines carry the data from raw to ready. The first stage subtracts biases and dark patterns, identifies cosmic rays, and corrects for nonlinearity in pixels nearing saturation. The second stage places the data in physical units and ties wavelengths to pixels. The third stage combines exposures, registers dithered frames, removes geometric distortion, and builds the mosaics and cubes that scientists will interrogate. Each correction carries an uncertainty. A proper pipeline tracks that uncertainty alongside the signal, propagating it through every operation so that error bars later reflect reality rather than hope. Spectra are harvested with care. A trace on a detector is followed with an extraction aperture, summing counts and subtracting the background measured nearby. In crowded fields, optimal extraction weights, pixels by expected profile shape, rescuing faint lines from beneath noise. Slit losses are corrected by modeling the point spread function across the detector and by measuring standard stars whose spectral shapes are known. Absolute calibration ties the flux scale to physical units by comparing instrument counts to celestial yardsticks with established brightness. Wavelength calibration is refined by skylines and by internal lamps whenever possible. The goal is a spectrum whose axes are trustworthy, where distance can be inferred from feature positions and physical conditions from ratios. In images, detection thresholds are set only after background statistics are understood. Matched filters amplify targets with shapes that mirror the point spread function. Photometry can be simple aperture sums, corrected for encircled energy, or it can be model fits to profiles that allow overlapping sources to share the light sensibly. Colors are assembled by aligning images from different filters with subpixel precision and by measuring flux in consistent apertures that account for different point spread functions as the wavelength changes. Tiny errors here slide directly into photometric redshifts, so the obsession with detail is warranted. Redshifts derived from photometry become probability distributions rather than single numbers. Templates representing galaxies with different ages, dust contents, and emission lines are shifted across color space until they match the measured fluxes in each filter. The match quality turns into a curve that rises where solutions fit and falls elsewhere. Priors enter cautiously, based on luminosity functions and the known distribution of galaxy types as a function of redshift. The final estimate is a weighted center of a curve whose width tells how humble the claim should be. Spectroscopic redshifts, when obtained, collapse the curve to a spike and free every other measurement from the uncertainty of distance. Physical properties are inferred through forward modeling. Population synthesis codes take an assumed star formation history, metallicity, and dust law and produce a spectral energy distribution. That distribution is processed through the instrument's filter curves to create synthetic photometry. A search algorithm compares synthetic to observed values, exploring a grid or sampling a prior space with Markov chains. The output is not a single mass or age, but a posterior distribution that reflects degeneracies. A young, dusty galaxy can masquerade as an older, cleaner one in certain bands, and the models refuse to forget it. Kinematics emerge from line profiles. A Gaussian might fit a quiet region, but double peaks, skewness, and broad wings are common. These shapes encode outflows driven by radiation and supernovae, inflows along cold streams, rotation in clumpy disks, and the damps imposed by residual neutral hydrogen. Fits with multiple components, return velocities, dispersions, and fluxes for each. Maps built from integral field cubes show where the components live. In some galaxies, the center is not the fastest part. A clump off to the side pumps a wind while the core turns more gently. Understanding requires accepting that small systems can be complicated. High contrast imaging benefits from algorithms that learn a star's stubborn signature. Reference differential imaging builds a library of similar stars and subtracts them, revealing companions. Angular differential imaging rotates the field during a sequence while leaving the instrument fixed, then constructs a model of the star's speckles to subtract. Spectral differential imaging uses the fact that speckles scale with wavelength while planets do not. Combining these methods with coronagraphic masks extracts light whose ratio to the star can be 1,000,000,000 to 1. Even if a planet is too cool to be bright, a ring of dust stirred by its gravity can betray its presence. Synergy among instruments multiplies confidence. An emission line measured at moderate resolution fixes a redshift that turns a broad break into an unambiguous distance. A mid-infrared detection of warm dust validates a high star formation rate inferred from ultraviolet light, or it contradicts it and forces a revision of dust assumptions. A non-detection in a specific line that should be strong under certain excitation rules out a black hole contribution in a compact core. A detection of a fine structure line at long wavelengths reconstructed into the same volume viewed in the infrared binds chemistry to structure. When multiple senses agree, the underlying physical picture tightens. Quality control is relentless. Artificial sources are planted into raw frames and asked to run the gauntlet of reduction. Their measured fluxes are compared to their planted values to calibrate completeness and bias. False positive rates are estimated by repeating the entire detection procedure on inverted images or noise realizations. Independent teams reprocess the same data with different choices to check that results are not artifacts of a single pipeline's temperament. Statistics are reported with clear priors, and provisional claims are labeled with the caution their foundations deserve. Time is the final ingredient. Repeat visits measure variability from accretion and from massive stars. Repeat spectroscopy checks whether lines shift as winds evolve or as new bursts ignite. Drift in flat fields and persisting artifacts are monitored and modeled. Over months and years, a program accrues not only depth, but a memory of its own performance. That memory turns into an ability to push thresholds without crossing into self-deception. Sensitivity improves as understanding improves. Machines listening to starlight are built on the premise that every photon counts and every assumption must be tested. Their poise in the cold, their clocks, their moving shutters, their whispering refrigerators, their software that knows the difference between a speck of dust and a galaxy at the edge of time, all of it serves a patient ambition. The ambition is to translate faintness into truth. By turning light into cubes and curves, into maps and likelihoods, the instruments let physical laws question themselves against reality. In that questioning, the first morning becomes less a myth and more a measured hour, recovered not by guesswork but by the craft of listening carefully and knowing what silence means. Surveys widen like tides. What began as a handful of deep pointings grows into a quilt that spans constellations, each tile stitched from patient exposures and careful calibrations. Programs with names that sound like seasons and distances carve the sky into volumes. Some magnified by chance alignments with massive clusters, others chosen for emptiness that is not truly empty. The yield is a census that tests every earlier suspicion. Bright counts are revised, faint slopes sharpen, line statistics settle towards stable ratios, and patterns in the distribution of sources turn from hints into measures. With each release, models are forced to breathe the same thin air as the data. Numbers sustain the reckoning. The luminosity function at youth sheds its early wobble and stands with a faint end steep enough to keep small galaxies in the story of transparency. The bright end still hosts overachievers, yet their frequency cools when lensing corrections are pressed harder and volumes grow. The cliff where neutral hydrogen erases the blue side of spectra slides in wavelength as predicted, but the depth of its damping wing now traces a map of ionization fraction across redshift with smaller error bars. Correlations between galaxies and faint fluctuations in the background begin to show that the clearing happened in a patchwork shaped by filaments rather than in isolated bubbles. Each statistic embeds its own uncertainties and is treated with the discipline they demand. Yet the combined chorus moves the narrative away from surprise and toward clarity. Reanalysis becomes a ritual of humility. Teams return to original frames, armed with improved flat fields, better persistence models, and revised treatments of scattered light. A few celebrated candidates fall below threshold once artifacts are recognized. Some borderline cases climb into confidence after deeper integration connects a thin line segment into a full profile. Masses derived from broadband fits slide downward when nebular continuum and line contamination are incorporated more carefully. Star formation rates shift when dust temperatures are constrained by longer wavelength data. The effect is not simply pruning, it is gardening. What survives has roots. Spectroscopy advances from reconnaissance to detail. Multiplex shutters draw thousands of thin rainbows across detectors in a single visit. Low-resolution modes confirm distances by catching the hydrogenscape around the resonance. Then medium-resolution modes carve ions into separate peaks that betray temperatures and densities. A few galaxies show lines so strong that simple stellar populations cannot explain them without invoking unusually hot radiation fields. Others show high ionization but muted mid-infrared dust, making a case for buried engines or diluted metallicity. Diagnostics once reserved for later cosmic times are ported into youth and adjusted for the different chemistry and pressures there. The diagrams that sort stars from accretion, shocks from photoionization, steady disks from turbulent inflows are redrawn in a new quadrant of parameter space. Clustering measurements expand in confidence. Angular separations turn into three-dimensional distances with enough precision to compute correlation functions that diagnose typical halo masses. Bias factors fall into ranges expected for rare peaks inhabiting heavy scaffolds. Large-scale features hint at residual ripples from primordial sound, faint yet persistent. Protoclusters step from rumors into catalogues, with membership lists and tentative velocity dispersions. In these embryonic cities, chemical enrichment appears ahead of the average schedule, dust warms earlier, and compact cores grow faster. Outliers become laboratories. The question shifts from whether such places exist to how they sculpt their residents. The ledger on accretion brightens with new entries. A larger fraction of candidates show high energy line ratios once samples grow. Stacks reveal weak X-ray signals where any single object would stay silent. Variability becomes a detectable statistic across populations, even when no one source presents a dramatic light curve. The black hole mass ladder in youth gains more rungs, and the distribution of masses begins to show a shoulder consistent with heavy seeds in rare environments and lighter seeds elsewhere. Evidence is uneven but cumulative, the kind of trend that refuses to vanish when analyzed separately by independent groups. Dust keeps complicating and completing the picture. Farther into the millimeter, arrays on the ground map far infrared glow over the same regions charted in the infrared. Cross-matching pulls hidden star formation out of shadow. In some fields, the energy budget swings decisively toward the obscured half. In others, ultraviolet light remains a good accountant. The relationship between ultraviolet slope and infrared excess wanders from the later universe's familiar track, with temperatures higher and geometry more porous. Models adapt by allowing clumping that opens windows in otherwise dusty structures, a compromise that raises the escape of ionizing photons without denying the presence of heavy grains. Synergy carries weight beyond romance. The widened quilt is draped across maps at other wavelengths that chart neutral hydrogen and trace faint lines from metals cooling in gas. Where galaxies cluster, the radio background dims as ionized regions grow. Where galaxies are sparse, the background remains bright and mottled. Intensity mapping picks up ensembles that individual detections miss, confirming that star formation at the faint end was common enough to matter even if the members cannot yet be listed by name. The union of methods raises confidence and reduces the temptation to let any one instrument tell the whole story. Disagreements walk in openly. A handful of massive candidates at extreme redshift retain their thrones even after careful accounting, insisting that assembly was wild in some corners. Others step down once emission lines that had inflated their colors are separated out. Acclaimed quiescent galaxy at Youth finds faint lines that betray ongoing formation once a deeper visit removes sky residuals. A putative metal-free signature yields to a blend of low metallicity and modest dust when medium-resolution spectra are taken. Each correction is less an embarrassment than a celebration of the system working as intended. The literature grows less dramatic in its headlines and richer in its tables. Theory meets these tables with models that now carry enough resolution and physics to be judged on details. Simulated halos fed by narrow filaments produce clumpy, dispersion-dominated disks whose line profiles begin to resemble those observed. Star formation histories with bursts layered on slow growth imitate the flicker seen in specific star formation rates. Feedback recipes tuned to create porous interstellar media deliver escape fractions that match those inferred from line ratios and continuum slopes. Direct collapse scenarios remain a minority pathway, yet their footprints show up in places where background radiation fields and dynamics allow them. Warm dark matter variants lose viability as lensing anomalies and satellite counts stay loyal to cold and granular scaffolds. Early dark energy remains a delicate adjustment whose breath must remain shallow to avoid breaking other measures. The reckoning is hard on grand revisions and generous to blended solutions. Catalogs join hands quietly. Independent teams cross-calibrate photometry, standardize filter curves, and release joint reductions for keystone fields. Disagreements over pipeline choices turn into shared test beds where planted sources and synthetic skies are used to measure bias. Conferences devote sessions to failure modes and to the psychology of detection thresholds. The social machinery of science proves as important as the mechanical machinery in orbit. Trust is built case by case, first on numbers, then on habits, then on a shared language for uncertainty. Time adds a new axis. Repeat observations extend baselines long enough to see structural change in a few fortunate systems. A lensed arc brightens as a caustic drifts across a clump. A line equivalent width declines as a burst ages. A core with signs of accretion fades and then returns, painting the first shaky light curves of engines at extreme distance. Even when changes are small, they anchor estimates of lifetimes, duty cycles, and fuel supply. The dawn acquires motion rather than just structure, a whisper of plot added to the setting. Lessons filter back into local neighborhoods. Nearby dwarf galaxies with low metallicity and high specific star formation rates become analogues for youth. Instruments return to them and hand over the same measuring sticks used at distance. Escape fractions are tested directly. Dust curves are drawn with mid-infrared precision. Winds are mapped as they break through shells. When similar behaviors are seen in both directions, confidence rises that interpretations are not artifacts of distance, but signatures of physics. The bridge between epochs becomes a two-way road where ideas cross and return refined. Noise reductions sharpen slowly, as expected in work that asks for truth at the edge of what detectors can register. Dark current maps improve, persistence traps are modeled with quasi-linear memory, stray light templates are updated after each thermal event. Micrometeoroid impacts, rare but consequential, are absorbed by small actuator adjustments that restore segment figures. The ability to take colder data rises as practice accumulates. Gains are incremental, yet mercifully cumulative. The reckoning extends to the calendar. Timelines of reionization from infrared signs meet those from long wavelength backgrounds in a convergence that narrows both. The mean redshift, where the universe becomes mostly transparent, settles within tight bounds, while the width of the transition reveals patchiness that agrees with models of clustered sources on a web. The cosmic star formation rate density curve acquires earlier points with real error bars rather than placeholders. The integrated photon budget becomes sufficient without invoking exotic contributors if faint galaxies are numerous and leaky, yet a non-trivial share from buried engines remains compatible with the totals. The balance is nuanced rather than doctrinaire. Through all of this, the tone of the endeavor matures. Awe yields ground to craft, and craft to method, and method to a quiet confidence that the history of the first morning can be written in prose that respects both beauty and measurement. Each correction is a kindness to truth. Each confirmed outlier is an invitation to think wider rather than louder. The reckoning is not closure, it is the slow alignment of instruments, ideas, and sky. In that alignment, the dawn becomes not only visible, but legible, a chapter with margins wide enough to annotate, and with ink dark enough to endure.